Hello there, and welcome to Life Beyond Seen, the little corner of the internet where curiosity slows down, the world gets a bit quieter, and strange corners of our planet are explored at a pace gentle enough to let the mind wander. Some nights we look at the stars, other nights we follow the winding paths of history or science, and sometimes we simply drift into the places on Earth that still feel a little mysterious. Tonight's journey takes us somewhere very cold, very distant, and surprisingly unexplored. Not a hidden jungle or a deep cave system, but a place many of us think we already understand. A place that appears on every classroom globe as a small white cap at the very top of the world. The North Pole. Now, at first glance, the North Pole doesn't look particularly mysterious. On most maps it appears as a smooth white patch surrounded by pale blue ocean, as if someone spilled a little milk across the Arctic and called it a day. It's often imagined as a flat expanse of ice, quiet, empty, perhaps with a lonely polar bear wandering across it and the occasional research station parked somewhere nearby. But the truth is a little stranger, because beneath that calm, frozen surface lies one of the least explored environments on Earth. A vast ocean hidden under shifting sheets of ice, a place where sunlight disappears for months at a time, where temperatures plunge far below freezing, and where life survives in ways that would seem impossible anywhere else. And within that hidden ocean are creatures that scientists have only just begun to discover. Animals living in darkness beneath meters of ice. Organisms thriving in pressure and cold so extreme that most life forms would simply stop functioning. Entire ecosystems quietly continuing their ancient routines far from human eyes. Some of these creatures were discovered only in the last few decades. Some have been seen only once, and some may still be waiting beneath the ice, completely unknown to science. It's an odd thought, really. In an age of satellites, deep-sea robots, and detailed maps of nearly every continent, the top of our own planet still holds secrets. So before we wander any farther into this frozen world, let me ask you something simple. Where in the world are you listening from tonight? Perhaps you're somewhere warm, wrapped in a blanket while rain taps gently against the window. Maybe you're in a quiet city apartment where the distant sound of traffic hums like a faraway ocean. Or perhaps you're already tucked into bed, letting the day slowly fade while a quiet voice talks about places most people will never visit. And whatever time it is in your little corner of the planet, it's probably very different from the rhythm of the North Pole. Up there, time behaves a little strangely. For several months each year, the sun never rises at all. The world remains locked in darkness, lit only by the pale shimmer of moonlight and the occasional dancing ribbons of the aurora borealis. Then, slowly, the sun returns, circling the horizon without ever truly setting, creating a long stretch of endless daylight. No mornings, no evenings, just a slow turning of the earth beneath the sky. If you find this kind of quiet exploration soothing, or simply enjoy drifting through curious scientific stories before sleep, feel free to leave a like on the video and perhaps subscribe. It helps this calm little channel reach others who might enjoy a gentle journey into the unknown as well. Now, let's begin at the edge of the world. Not on a map, but in reality. The North Pole is not land. That surprises many people at first. Unlike the South Pole, which sits firmly on the continent of Antarctica, the North Pole rests on floating sea ice above the Arctic Ocean. Imagine a frozen ocean stretching thousands of kilometers in every direction. Ice sheets drift slowly across the water, pushed by winds and currents, sometimes colliding, sometimes breaking apart, sometimes stacking into ridges several meters high. And at the very centre of that shifting, frozen expanse lies the geographic North Pole. But despite its fame, reaching that point was not easy. For most of human history, the Arctic Ocean remained one of the most hostile environments on Earth. Early explorers who ventured north found themselves battling freezing temperatures, crushing ice fields, and a landscape that constantly moved beneath their feet. Unlike mountains or deserts, the Arctic had no fixed terrain. The ice itself drifted. Paths that seemed safe one day could split open the next, revealing dark seawater below. Ships attempting to travel north often became trapped. The sea ice closed around their hulls like slow-moving jaws. Some expeditions survived only by abandoning their vessels and trekking across the ice on foot, dragging sledges filled with supplies. Others were less fortunate. Yet curiosity is a powerful thing. Throughout the 19th and early 20th centuries, explorers from several nations attempted to reach the North Pole. Some journeys became legendary tales of endurance. Others ended in tragedy, ships lost to the ice, and crews vanishing into the frozen silence. One of the challenges they faced was something quite simple. No one knew what actually existed at the top of the world. Some believed the Arctic might contain open water, an ice-free sea hidden beyond the outer ring of pack ice. Others imagined strange ecosystems thriving beneath the frozen surface. A few even speculated about entirely unknown animals living in the polar depths. At the time, these ideas sounded fanciful. The Arctic seemed far too cold, far too dark, and far too isolated to support much life at all. But science has a habit of surprising us. Beneath the Arctic ice flows a deep ocean basin thousands of meters deep. The water there is cold, certainly, but not lifeless. In fact, the Arctic Ocean connects to the Atlantic and Pacific Oceans through narrow passages, allowing currents to circulate nutrients and microscopic life across vast distances. And where there are nutrients, life tends to follow. Even under thick ice, microscopic algae manage to grow during the brief Arctic summer, clinging to the underside of the ice sheets like a thin green carpet. These tiny organisms capture sunlight when it returns after the long winter darkness, forming the base of a complex food chain. Small crustaceans feed on the algae. Fish feed on the crustaceans. Seals hunt the fish. And occasionally, far above it all, a polar bear may pause at the edge of a breathing hole, waiting patiently for a seal to surface. But that familiar Arctic scene tells only a small part of the story. Because most of the Arctic Ocean lies far deeper than those shallow coastal waters. In many places the seafloor plunges several kilometres below the ice. Down there sunlight never reaches. The pressure is immense. Temperatures hover near freezing. And yet, life still persists. The deeper scientists explore the Arctic, the more unusual the creatures they discover. Some resemble animals we already know, only adapted to extreme cold. Others look so strange they seem almost alien. Translucent fish with antifreeze chemicals in their blood. Giant amphipods the size of a human hand drifting slowly across the dark sea floor. Delicate sea spiders with legs stretching wider than a dinner plate. These animals survive in conditions that would quickly kill most familiar species. Their bodies have evolved over millions of years to function in icy water, low oxygen levels, and near-permanent darkness. And perhaps the most remarkable part of this story is how recently many of them were discovered. For centuries, humans could only explore the surface of the Arctic. Thick ice prevented ships from reaching much of the ocean, and diving beneath the ice was nearly impossible with early technology. Only in the last few decades have researchers begun sending robotic submarines and remote cameras under the ice to see what lives there. What they found was not an empty ocean, it was a living one. Slow-moving creatures gliding across the seabed, strange gelatinous organisms drifting like pale lanterns through the water, and ecosystems built around food sources scientists are still trying to understand. Some discoveries came as complete surprises. In 2007, researchers exploring beneath Arctic ice discovered entire communities of organisms living on the underside of thick ice shelves, feeding on algae that had never been studied before. In another expedition, cameras lowered deep into the Arctic basin recorded unfamiliar species of fish and invertebrates that did not match anything previously documented. Each discovery raises a curious possibility. If so many new species have been found in such a short time, what else might still be waiting beneath the ice? The Arctic Ocean covers more than 14 million square kilometres. Much of it has never been directly observed. And that brings us back to the quiet mystery hiding beneath the North Pole, because the frozen surface we imagine as empty is really more like a ceiling above a hidden ocean world, an environment shaped by darkness, pressure, cold, and time. A place where evolution has taken unusual paths, where creatures survive in ways that would seem impossible elsewhere, and where scientists still lower cameras into the black water, not entirely sure what might drift into view. Some nights the ocean below the ice is completely silent. Other nights hydrophones placed beneath the ice record distant sounds moving slowly through the water, low pulses, faint echoes, strange calls carried across kilometres of dark sea. Some of those sounds belong to whales navigating beneath the ice. Others come from shifting ice plates grinding together above the water. But a few recordings remain unexplained. Not necessarily mysterious in a dramatic sense. The ocean produces many unfamiliar sounds after all. Still, the Arctic is vast enough that even now, with modern technology, humans have explored only small parts of it directly, which means somewhere beneath those drifting sheets of ice there are almost certainly creatures alive today that no human has ever seen. Animals following ancient survival patterns beneath the frozen ceiling of the Arctic Ocean. Creatures adapted to a world where sunlight disappears for months at a time. Life continuing quietly in a place most of us will never visit. And to understand how such a hidden ecosystem could exist for so long without human observation, it helps to step back and consider just how difficult it has always been to reach the North Pole in the first place. Far to the north of most human settlements, beyond forests, beyond tundra plains, beyond even the last scattered villages where people still live with the rhythm of long winters and short summers, the landscape slowly begins to change. Trees disappear first, then shrubs become sparse. Eventually even hardy grasses give way to a terrain of snow, wind and frozen sea. The Arctic is often imagined as a place of dramatic storms and roaring blizzards, and sometimes it is. But much of the time it feels strangely calm, quiet in a way that is difficult to experience anywhere else on Earth. Imagine standing on a wide plain of ice that stretches so far in every direction that the horizon seems almost unreal. The ground beneath your feet is not land but frozen ocean, a shifting sheet of white resting on dark water thousands of meters deep. The sky above might be pale grey or soft blue, or glowing faintly with the low winter sun that never climbs very high. And then there is the silence. Not the everyday quiet of a library or an empty park, a deeper silence created by distance, cold, and the absence of almost everything familiar. No insects buzzing, no rustling leaves, no distant traffic. Even the wind often moves slowly here, sliding across the ice with a gentle whisper rather than a roar. In those moments, the Arctic can feel almost suspended outside the normal world. For centuries, this silence helped hide what lay beneath the ice. People have lived along the edges of the Arctic for thousands of years. Indigenous communities such as the Inuit, the Sami, the Nenets, and many others learned how to travel across frozen seas, hunt in extreme cold, and read subtle signs in the landscape that outsiders might miss entirely. They knew the Arctic was not empty. Seals moved beneath the ice. Fish travelled through cold currents below. Occasionally whales passed through narrow openings where the ice cracked apart. But even the most experienced hunters rarely saw what lived deeper in the Arctic Ocean itself. Thick ice formed a barrier between the human world above and the dark ocean below, and that barrier was not easy to cross. Sea ice at the North Pole forms through a slow process repeated each winter. As the air temperature drops, the surface of the Arctic Ocean begins to freeze. At first, a thin layer of ice appears like glass spreading across the water. Gradually, that layer thickens as more seawater freezes onto the underside. Over weeks and months, the ice becomes strong enough to support snow, wind-blown ridges, and eventually the weight of explorers or animals moving across it. But it never becomes truly permanent. Unlike land-based glaciers or ice sheets, sea ice floats. Winds and ocean currents constantly push it across the Arctic Ocean. Large pieces drift together and collide, sometimes piling into jagged ridges several meters high. Other times, wide cracks appear where the ice pulls apart, revealing dark seawater below. These openings are known as leads, and they form temporary windows into the hidden ocean beneath. For a seal or a whale, a lead is essential. It allows them to breathe. For an explorer travelling across the Arctic ice, however, a sudden lead can become a dangerous obstacle. Imagine walking for hours across a flat white landscape, only to reach a narrow channel of black water stretching across your path. In winter, that water might freeze again overnight, but it might also widen or drift away with the moving ice. The Arctic surface is constantly changing. Early explorers who ventured north discovered this quickly. Maps suggested the North Pole was a fixed location, but the ice around it behaved more like a slow-moving puzzle. Paths opened and closed unpredictably. Ice flows shifted beneath camps. Supplies stored carefully one evening might be carried several kilometers away by morning as the ice drifted. And beneath all of it was the Arctic Ocean, largely unseen. The first scientific clues about what lived below came not from direct observation, but from simple tools lowered through holes in the ice. In the late 19th century, researchers began drilling narrow openings and lowering weighted lines to measure ocean depth. These early soundings revealed something surprising. The Arctic Ocean was much deeper than anyone expected. In many places, the seafloor dropped several thousand meters below the surface ice. Instead of a shallow basin filled with ice, the North Pole rested above a vast ocean with underwater ridges, plains, and deep valleys. It was, in every sense, a hidden world. But knowing that an ocean existed beneath the ice did not immediately reveal what lived inside it. For a long time, scientists assumed the Arctic depths might be nearly lifeless. Cold water slows biological processes, and sunlight barely penetrates the thick ice cover. Without sunlight, photosynthesis becomes difficult, which means the entire food chain might struggle to exist. At least that was the theory. Reality turned out to be much more complicated. The Arctic Ocean connects to other oceans through narrow passages. One lies between Greenland and Norway, allowing water from the Atlantic to flow northward. Another connection exists through the Bering Strait between Alaska and Russia, where Pacific water enters the Arctic basin. These currents carry nutrients, microscopic organisms, and small animals into the Arctic environment. Even beneath heavy ice, tiny algae manage to grow during the brief summer when sunlight returns to the polar sky. These microscopic plants attach themselves to the underside of sea ice, where light can still reach them. To the human eye, the ice above looks perfectly white and empty. But underneath it may host thin films of life that stretch across wide areas like invisible meadows. Small crustaceans graze on the algae. Larger creatures feed on those crustaceans. Energy slowly moves through the food chain, even in water that hovers just below freezing. But observing these processes directly was nearly impossible for most of human history. The thickness of Arctic ice often exceeds 2 meters. In some areas, pressure ridges pile the ice much higher. Breaking through that frozen ceiling required tools and techniques early explorers simply did not have. Divers could not easily enter the water because freezing temperatures quickly drained body heat. Even if someone managed to descend beneath the ice, the darkness and lack of clear pathways back to the surface made such attempts extremely dangerous. It was like trying to explore a cave system where the ceiling could shift at any moment. For decades, scientists had to rely on indirect evidence. They collected water samples through drilled holes. They dragged nets slowly beneath the ice, hoping to catch small animals drifting in the currents. Occasionally unusual species appeared in those nets, creatures with pale bodies and strange shapes adapted to life in cold darkness. Each discovery hinted that the Arctic Ocean contained far more life than anyone had imagined. Still, most of the environment remained hidden. The surface silence of the Arctic reinforced that mystery. When standing on the ice, the landscape gives almost no indication that an ocean full of activity lies just below. Wind moves snow across the ground in soft patterns. Sometimes distant ice ridges creak as they shift under pressure. If the weather is calm, even those sounds fade until the world feels almost completely still. In winter darkness, the silence becomes even more pronounced. For several months each year the sun never rises above the horizon at the North Pole. The sky glows faintly during midday twilight before slipping back into night. Temperatures drop far below freezing, sometimes approaching minus 40 degrees Celsius. During those long nights the ice thickens further, sealing the ocean beneath an even stronger barrier. Yet below that frozen roof, life continues. Fish swim slowly through cold currents. Crustaceans drift in dark water. Strange, gelatinous organisms pulse gently as they move, their bodies almost invisible in the blackness. Sound travels efficiently through water, so animals beneath the ice communicate across distances impossible in air. Whales navigating the Arctic sometimes sing complex songs that echo through the hidden ocean for kilometers. Occasionally those sounds reach the ice above. Explorers camping on thick sea ice have reported hearing distant vibrations or faint knocking noises travelling upward from the water below. The ice acts like a giant amplifier, carrying underwater sounds across wide areas. To someone unfamiliar with the Arctic, those noises can feel eerie, but most belong to natural activity beneath the frozen surface. Ice itself produces sound as well. When temperatures shift or wind pushes large floes together, the ice plates grind slowly against one another. Deep cracks form with sudden booming noises that travel across the landscape. These sounds remind anyone standing there that the Arctic is not a solid continent, but a moving mosaic of frozen ocean. That constant motion is another reason so much of the Arctic remained unexplored for so long. Ships travelling north had to contend not only with freezing temperatures, but with the slow crushing pressure of drifting ice. Wooden hulls built for open seas often splintered when trapped between large floes. Entire expeditions were lost when ice closed around vessels and carried them away for months or years. The famous voyage of the ship Fram in the late 19th century used a different strategy. Rather than fighting the ice, the ship was designed to drift with it. Explorers allowed the vessel to freeze into the pack ice and slowly float across the Arctic Ocean with natural currents. During that drifting journey, scientists collected valuable data about ocean depth, temperature, and currents beneath the ice. But even then, they could only glimpse small pieces of the larger picture. It would take another century before technology allowed humans to explore beneath Arctic ice directly. Submersible robots, remote cameras, and advanced sonar systems finally made it possible to observe the ocean environment without risking human divers in freezing water. When the first cameras descended into the dark Arctic depths, scientists expected to see little more than empty water and scattered marine life. Instead, they discovered something remarkable: entire communities of organisms living quietly beneath the ice. Creatures adapted to cold in ways researchers were still trying to understand. Species so unfamiliar that identifying them sometimes required years of careful study. The silence of the Arctic surface had hidden an active ecosystem all along, and the more scientists explored, the clearer it became that the Arctic still held many secrets. Even today, large areas of the Arctic Ocean floor have never been observed directly. Ice cover, harsh weather, and the sheer scale of the region make exploration difficult and expensive. Robotic vehicles travel beneath the ice for limited periods before returning to the surface. Satellites can map the ice above but reveal little about what moves in the water below. In other words, the white silence of the Arctic remains a kind of disguise. From above it appears simple, a frozen ocean stretching to the horizon. But beneath that quiet surface lies a world shaped by darkness, pressure, cold, and time. Creatures drift through water older than most human civilizations. Life persists in ways that continue to surprise researchers every year, and understanding why so much of this hidden ecosystem remained undiscovered for centuries requires looking at the long history of exploration in the far north, where generations of explorers tried to reach the very centre of the frozen ocean and often found themselves facing conditions far more difficult than they'd imagined. For most of human history, the North Pole was not simply a distant place. It was a place almost entirely outside human reach. Maps showed it clearly enough, a neat point at the very top of the planet, but in reality it was surrounded by one of the most difficult environments anyone could attempt to cross. To understand why so much of the Arctic remained unseen for so long, it helps to imagine what explorers were actually facing. The Arctic Ocean does not behave like a typical ocean. In warmer regions, ships move freely across open water, guided by coastlines, currents, and predictable weather patterns. The Arctic works differently. Much of the ocean is covered by sea ice that constantly shifts, breaks, and reforms. That ice is never truly stable. From a distance it may appear smooth and solid, but in reality it behaves more like a slowly drifting puzzle of frozen plates. Large flows can stretch for kilometres. Wind and currents push them together or pull them apart without warning. Thick ridges form where sheets collide, while wide cracks appear when they separate. Anyone attempting to travel across that surface is moving on something that never stops changing. The first explorers who pushed northward quickly learned this lesson. In the 18th and 19th centuries, ships trying to reach the Arctic often became trapped when ice closed around their hulls. Once the sea froze solid, vessels could no longer move. Crews were forced to wait months for summer thaw, hoping the ice would release them. Sometimes it did. Other times the ice crushed ships slowly, splintering wood and bending metal until the vessel was lost completely. Even when ships survived, reaching the central Arctic remained extremely difficult. The farther north explorers travelled, the thicker and more unpredictable the ice became. Navigation through narrow channels between ice flows required constant vigilance. A path open one day might close the next as winds shifted and pushed the ice together. Many expeditions spent entire seasons simply searching for safe routes through the frozen maze, and that was only the beginning of the problem. Extreme cold added another layer of difficulty. Arctic temperatures routinely drop below -30 degrees Celsius in winter, and even during the brief summer, they rarely climb far above freezing. Metal becomes brittle. Mechanical systems fail. Fuel thickens in engines. Skin exposed to the air for too long risks frostbite. Clothing helped, of course, but early explorers did not always understand how to dress properly for such conditions. Indigenous Arctic communities had developed highly effective clothing systems using animal furs and layered garments designed to trap warm air. Many early European expeditions arrived with heavy wool uniforms and equipment poorly suited for extreme cold. The results were often uncomfortable at best and dangerous at worst. Cold also affected the simple act of travelling. Walking across snow and ice consumes far more energy than walking on solid ground. Sledges carrying supplies had to be dragged by hand or pulled by dogs. Progress was slow and exhausting. Even short distances could take hours, and every mile travelled north increased the risk of becoming stranded. Food supplies posed another challenge. Long journeys required large amounts of provisions, but carrying enough food for months of travel was difficult. Early expeditions often relied on preserved meats, dried biscuits, and canned goods that could survive freezing temperatures. But these foods sometimes lacked essential nutrients. Scurvy, a disease caused by vitamin C deficiency, plagued many polar expeditions. Symptoms included fatigue, swollen gums, joint pain, and eventually organ failure. Entire crews became weakened after months in the Arctic, making travel even harder. Later explorers learned to include fresh meat from seals or other animals when possible, which helped prevent the disease. But reaching hunting grounds was not always easy on drifting sea ice. All of these factors combined to make the Arctic one of the most challenging environments humans had ever attempted to explore. And then there was the darkness. Near the North Pole, the sun disappears completely for several months each year. During this polar night, the sky remains dim even at midday, only moonlight, starlight, and the occasional glow of the aurora illuminate the landscape. Travelling in such darkness was dangerous. Crevasses in the ice could be difficult to see. Snowstorms could reduce visibility to almost nothing. Without clear landmarks, navigation relied heavily on compasses and celestial observations. Yet compasses become unreliable close to the magnetic poles, where Earth's magnetic field behaves differently. In other words, the very tools explorers depended on could fail them in the far north. These obstacles explain why it took so long for anyone to even approach the geographic North Pole. For centuries, the Arctic remained largely unknown to the wider world. Stories circulated among sailors and scholars about what might exist beyond the outer ring of ice. Some imagined a vast open sea surrounding the pole, warmed by ocean currents. Others speculated about hidden islands or unknown continents. The reality turned out to be both simpler and more complicated. The Arctic is primarily an ocean covered by seasonal ice, but that ice creates an ever-changing barrier between the surface world and the water below. Even if someone managed to reach the central Arctic, exploring beneath the ice remained another challenge entirely. The thickness of sea ice varies from year to year, but in many regions it reaches 2 to 4 meters deep. In places where ice ridges form, stacked layers can extend much farther. Breaking through that frozen ceiling required tools and techniques that early explorers simply did not possess. Drilling holes through the ice was possible, but only for small openings. Lowering equipment through those holes allowed scientists to collect water samples or measure depth. Yet it revealed very little about the living creatures moving in the surrounding ocean. Direct observation remained out of reach. Divers face serious risks in Arctic water. Temperatures close to freezing quickly drain body heat, and heavy ice above makes returning to the surface complicated. Without modern dry suits, specialized breathing equipment, and support teams monitoring conditions, underwater exploration beneath sea ice was extremely dangerous. For most of history it was simply not attempted. That meant the Arctic Ocean remained hidden in a literal sense. Humans could stand above it, walk across its frozen surface, even drill small holes into the water below, but they could not easily see what existed beneath the ice. The ocean floor was another mystery. Early depth measurements revealed that the Arctic basin contained deep valleys and underwater ridges stretching across the seafloor. But mapping those features required careful sonar surveys conducted from ships capable of surviving icy conditions. Even with modern technology, charting the Arctic seabed has been slow work. Large areas remain only roughly mapped today. Weather also played a role in keeping the region hidden. Arctic storms can form quickly as cold air masses interact with shifting ocean currents. Strong winds push ice across the water, closing navigation routes and creating dangerous pressure ridges. Visibility can drop dramatically when snow begins to blow across the landscape. Explorers caught in these storms sometimes had to stop moving entirely and wait for calmer conditions. Weeks could pass before travel became possible again. This unpredictability discouraged many attempts to reach the pole. Expeditions required enormous preparation, careful timing, and a willingness to accept significant risk. Even when explorers managed to reach extremely high latitudes, confirming their exact position proved difficult. Before the age of satellite navigation, determining latitude near the pole required complex astronomical observations. Cloud cover often prevented those measurements. As a result, several early claims of reaching the North Pole remain debated among historians. Some explorers believed they had arrived at the geographic pole only for later analysis, to suggest they were still many kilometers away. The drifting ice made precise location tracking even harder. While explorers walked across what appeared to be stable ground, the ice beneath them might slowly move with ocean currents. Someone travelling north all day could unknowingly drift south overnight. In the early 20th century, explorers like Robert Peary and Frederick Cook attempted to reach the pole using sledges and teams of dogs. Their journeys became famous examples of human endurance in extreme environments. But even these expeditions spent years preparing, and their routes crossed some of the most hazardous terrain on Earth. and once again, their focus remained on reaching the surface location of the pole itself. What lived beneath the ice was still largely unknown. It wasn't until the mid-20th century that technology began to change the situation. Submarines capable of travelling under Arctic ice provided the first opportunity to explore the hidden ocean more directly. In 1958, the nuclear-powered submarine USS Nautilus famously travelled beneath the Arctic ice cap, passing directly under the North Pole. For the first time, humans had navigated through the dark waters beneath the frozen surface. Although that journey was primarily a military demonstration, it also revealed how vast and complex the under-ice environment truly was. Later scientific missions used specialised submarines and remotely operated vehicles to collect data from beneath the ice. Cameras captured glimpses of the seafloor. Instruments measured water temperature, salinity, and currents. Occasionally, these missions also recorded unfamiliar marine life drifting through the water. Each discovery suggested that the Arctic Ocean hosted far more biological diversity than previously believed. Still, exploration remained limited. Robotic vehicles could only travel short distances before needing to return to their launch point. Thick ice sometimes prevented retrieval if weather conditions changed. Equipment failures in freezing water were common. Researchers had to plan each mission carefully, often waiting months for favourable conditions. Even today, studying the Arctic environment requires cooperation between international research teams, specialised ice-breaking ships, and advanced technology capable of functioning in extreme cold. Compared to other oceans, the Arctic remains one of the least explored marine environments on Earth. Ironically, this long history of difficulty has helped preserve some of the region's secrets. While humans mapped much of the planet during the last few centuries, the Arctic quietly continued its own rhythms beneath the ice. Creatures adapted to cold water evolved in isolation. Ecosystems formed around sources of nutrients drifting through the dark ocean. Many species remained unknown simply because no one had been able to observe them directly. And that raises an interesting point. Even now, in an age of satellites and underwater drones, scientists estimate that a large portion of Arctic marine life has yet to be documented. Some species may live deep in valleys along the ocean floor where few research vehicles have travelled. Others may exist beneath thick multi-year ice that remains difficult to penetrate. In other words, the North Pole remained unseen for so long, not because humans lacked curiosity, but because nature had placed an enormous barrier around it. Cold, darkness, drifting ice, and vast distances combined to protect the Arctic from easy exploration. Only recently have tools become powerful enough to begin revealing what lies beneath that frozen surface. And the more researchers look, the more they realise that the Arctic still contains entire ecosystems that science is only beginning to understand. Which makes the early journeys into this frozen ocean all the more remarkable, because long before submarines and robotic cameras existed, explorers set out across the ice with little more than sledges, compasses and determination, hoping to reach a point at the very top of the planet that no human had ever seen. For most of human history, the far north existed as a blank space on maps. Cartographers would often fill that empty region with simple labels such as terra incognita, or with small decorative drawings of sea monsters and wandering ships. It wasn't necessarily because people believed monsters lived there. Rather, it was an honest admission that almost nothing was known about that part of the world. The Arctic lay far beyond the everyday routes of trade and travel. Long before scientists lowered instruments beneath the ice, or submarines travelled under the polar cap, the only way to explore the region was the slow and uncertain method of physical travel. Ships had to move through freezing seas. Sledges had to cross drifting ice. Every mile required patience, planning, and a willingness to face conditions that could change without warning. Yet curiosity about the far north existed long before the age of modern exploration. Ancient Greek scholars already speculated about what might lie near the top of the world. They imagined a distant northern region called Hyperborea, a mythical land beyond the cold winds. Roman writers described frozen seas where daylight behaves strangely and winter seemed to stretch endlessly. These accounts were not based on direct observation, but on second-hand stories carried by traders who travelled along the northern edges of Europe. For centuries, those stories remained the closest thing to knowledge about the Arctic. In reality, the first people who truly understood the far north were the indigenous communities who lived along its borders. The Inuit across Greenland and northern Canada, the Sami across Scandinavia, and many other Arctic cultures developed ways of living with the environment rather than trying to conquer it. They built clothing from animal skins designed to trap warm air while allowing moisture to escape. They travelled across snow using sledges pulled by dogs. They learned to recognise safe sea ice and dangerous thin ice simply by reading subtle patterns in the snow and wind. For them, the Arctic was not an empty wilderness, it was a home. But their knowledge did not always reach the wider world. European explorers entering the Arctic often brought their own assumptions and technologies, sometimes overlooking the wisdom of those who had lived there for generations. The age of Arctic exploration began to accelerate during the 16th and 17th centuries when European nations searched for new trade routes. One idea became particularly appealing: the possibility of a northern sea passage connecting the Atlantic and Pacific Oceans. If such a route existed, ships could travel between Europe and Asia far more quickly than by sailing around Africa or South America. The map seemed simple enough. Sail north, pass through the Arctic Ocean, and emerge on the other side of the world. Reality proved far less cooperative. Early explorers sailing north from Europe encountered heavy sea ice long before reaching the pole. Their ships, built for open oceans, struggled to navigate narrow channels between floating ice floes. Sometimes they became trapped for weeks, surrounded by frozen water stretching to the horizon. One of the earliest explorers to push deep into Arctic waters was the English navigator Martin Frobisher in the late 16th century. Frobisher hoped to find the Northwest Passage through the Canadian Arctic. Instead, he encountered thick ice, unfamiliar coastlines, and weather conditions far harsher than anyone in his crew expected. Although he never reached the pole, his voyages revealed just how complex the Arctic landscape truly was. Other explorers followed similar paths. Henry Hudson sailed north in the early 17th century, searching for a route through the ice. His expeditions charted parts of the Arctic Ocean and several northern coastlines. But Hudson also discovered that ice did not behave like land or water in predictable ways. Entire stretches of sea could freeze solid while nearby channels remained open. Wind could close a path behind a ship as quickly as it had opened. Progress often depended less on navigation skill and more on patience. These early journeys revealed an important truth. Reaching the Arctic was possible. Understanding it would be much harder. By the 19th century, the desire to explore the far north had become something of an international challenge. Nations across Europe and North America sponsored expeditions to chart the Arctic Ocean, search for lost passages, and perhaps reach the North Pole itself. One of the most famous expeditions of that era was led by Sir John Franklin in 1845. Franklin set out with two ships, HMS Erebus and HMS Terror, hoping to complete the final unexplored section of the Northwest Passage. His ships carried advanced equipment for the time. They had reinforced hulls designed to withstand ice pressure, and even early steam engines to assist with navigation. Despite these preparations, the expedition vanished. Years passed with no word from Franklin or his crew. Search parties eventually discovered scattered clues across the Canadian Arctic, including abandoned camps and personal belongings left behind in the snow. Later evidence suggested the ships had become trapped in ice. The crew attempted to travel south on foot but faced severe conditions and limited supplies. The Franklin expedition became one of the most haunting stories in Arctic exploration. Yet even tragedies like this did not stop others from venturing north. One reason was simple human curiosity. Another was the growing belief that reaching the geographic North Pole would become one of the great achievements of exploration, much like climbing the highest mountains or crossing vast deserts. But reaching the pole meant travelling across sea ice rather than land. That created a unique set of challenges. Unlike solid ground, sea ice drifts with ocean currents. Large flows can move several kilometres each day depending on wind direction and water flow beneath the surface. An explorer could spend hours walking north only to discover that the ice beneath them had slowly drifted south overnight. This drifting effect meant that even a successful journey required careful calculations and constant adjustments. One of the explorers who approached the Arctic with unusual patience was the Norwegian scientist and adventurer Fridtjof Nansen. In the 1890s, Nansen developed a strategy based on careful observation of ocean currents. He believed the Arctic ice naturally drifted across the polar basin from Siberia toward Greenland. Instead of fighting the ice, he planned to use it. Nansen built a ship called Fram, specially designed with a rounded hull that allowed ice pressure to push the vessel upward rather than crush it. The plan was simple in concept but bold in execution. He would sail into the Arctic, allow the ship to freeze into the pack ice, and then drift with the natural movement of the ice across the ocean. For months the ship remained trapped in frozen water. But rather than panicking, Nansen and his crew treated the drift as part of the journey. They collected scientific data, measured ocean depth, studied weather patterns, and carefully tracked their movement across the Arctic basin. Eventually, Nansen attempted to reach the pole by leaving the ship with sledges and dogs, travelling across the ice with a companion named Hjalmar Johansson. They did not reach the pole itself, but they came closer than almost anyone before them. More importantly, Nansen's expedition revealed valuable information about the Arctic Ocean. His observations confirmed that the ice did indeed drift across the basin, and that deep ocean water existed beneath the frozen surface. This knowledge would guide later explorers. In the early 20th century, the race to reach the North Pole intensified. American explorer Robert Peary spent years travelling through the Arctic, learning from Inuit communities and adapting his equipment to survive extreme conditions. He used sledges pulled by dogs and established supply camps along his route. In 1909, Peary announced that he had reached the geographic North Pole. His claims sparked both celebration and debate. Some historians believe Peary did indeed reach the pole. Others argue that navigation errors may have placed him several kilometres away. Determining exact positions on drifting sea ice with the tools available at the time was extremely difficult. Regardless of the final verdict, Peary's expedition demonstrated how determined explorers had become. The far north was no longer an unreachable mystery, yet even as humans began standing near the pole itself, the ocean beneath the ice remained largely unexplored. Explorers walked across the frozen surface, set up camps, and recorded observations about weather and ice conditions. They occasionally drilled holes through the ice to collect water samples or measure depth, but they could not easily descend into the ocean below. For the creatures living beneath the ice, these human journeys probably passed unnoticed. Fish swam through dark currents. Small crustaceans drifted along underwater ridges. Strange gelatinous organisms pulsed slowly in the cold water. The explorers above were only temporary visitors in a world that had existed for millions of years. As the 20th century progressed, new technologies slowly expanded the reach of Arctic exploration. Aircraft allowed researchers to fly over regions once accessible only by ship or sledge. Later, ice-breaking vessels capable of cutting through thick sea ice opened new pathways for scientific expeditions. And eventually, submarines entered the story. When the first submarines travelled beneath Arctic ice, they revealed something extraordinary. The frozen surface that had challenged explorers for centuries was only a thin barrier above a vast ocean basin. Beneath it lay underwater mountain ranges, deep plains, and ecosystems that scientists had barely begun to study. Those early explorers had stepped into the frozen unknown with little more than courage and curiosity. They could not have imagined that far below their camps, beneath meters of solid ice, Entire communities of creatures were moving quietly through dark water. Nor could they have known that future scientists would one day lower robotic vehicles into that hidden ocean and discover species no human had ever seen. And as researchers continued to explore those depths, they began to realize that the Arctic Ocean was not simply cold and empty, but filled with life adapted to some of the most unusual conditions on Earth. Standing on Arctic sea ice, it is easy to imagine that very little exists beneath it. The surface appears empty. White ice stretches toward the horizon, occasionally broken by blue shadows or ridges of piled snow. The air is cold enough to quiet almost every sound, and the frozen ocean gives no obvious sign that anything lives below. Yet beneath that still surface lies an ocean that supports a surprisingly complex web of life. The Arctic Ocean is the smallest of Earth's major oceans, but it is far from barren. Beneath the ice, a layered ecosystem stretches from the underside of the frozen surface all the way down to seafloors thousands of meters deep. Each level supports different creatures adapted to conditions that would challenge most life forms. To begin understanding what lives there, it helps to start with the part of the Arctic environment that few people ever see, the underside of the ice itself. Although the top of Arctic ice looks solid and lifeless, the bottom surface often hosts thin films of algae. These microscopic organisms grow where faint sunlight filters through the ice during the Arctic spring and summer. Even a small amount of light is enough for them to perform photosynthesis. These algae form the first step in a food chain that supports much larger animals. When sunlight returns after the long polar winter, the algae multiply quickly along the ice underside. The layer is usually only a few millimeters thick, but it stretches across vast areas of ice. Small crustaceans gather there to feed. One of the most common of these animals is a tiny shrimp-like creature known as an amphipod. Amphipods cling to the ice using small hooked legs, while grazing on algae and organic material trapped in the ice. To the human eye, they are small, often only a few centimeters long. But in Arctic ecosystems, they play a large role. Many fish species rely on amphipods as an important food source. Drifting nearby are copepods, even smaller crustaceans that resemble moving specks under a microscope. Despite their size, copepods are among the most abundant animals in the Arctic Ocean. Some species store large amounts of fat inside their bodies, allowing them to survive long periods without food during the dark winter months. These tiny animals might seem insignificant, yet they form the foundation of Arctic marine life. Fish arrive next in the food chain. Several species have evolved specifically to survive beneath Arctic ice. One of the most remarkable is the Arctic cod. This small fish rarely attracts attention outside scientific circles, yet it may be one of the most important animals in the Arctic ecosystem. Arctic cod possess special proteins in their blood that act like natural antifreeze. These proteins prevent ice crystals from forming inside their bodies, allowing them to survive in water that hovers just below the freezing point of seawater. Without that adaptation, their cells would freeze and rupture. Arctic cod often swim close to the underside of sea ice where they feed on amphipods and copepods. In turn, they become prey for larger animals including seals, whales and seabirds. They are, in a sense, a bridge connecting microscopic life to the larger animals most people recognize. Moving deeper into the Arctic waters reveals creatures that appear increasingly unusual. Some fish species living in cold oceans have transparent or nearly transparent bodies. Their tissues allow light to pass through them, making them difficult to see in dim water. This kind of camouflage helps them avoid predators. Others rely on slow movements and energy conservation. In cold environments, metabolism slows significantly, meaning animals grow more slowly and may live longer than similar species in warmer seas. But fish are only one part of the Arctic underwater world. Drifting slowly through the water column are gelatinous animals known as comb jellies and jellyfish. Their bodies are soft and nearly transparent, shaped like floating bells or ribbons. comb jellies move using rows of tiny hair-like structures called cilia. When light strikes those rows at certain angles, they create shimmering patterns that look like rainbow waves moving along the animal's body. In the darkness beneath Arctic ice, that glow can appear almost otherworldly. Some of these gelatinous creatures are predators. They trap smaller organisms with sticky tentacles or specialized feeding structures. Others drift slowly through the water, filtering microscopic food particles from the surrounding currents. Because their bodies contain very little solid tissue, gelatinous animals rarely leave fossil records. Scientists often discover new species simply by lowering cameras into unexplored areas of ocean. The Arctic Ocean has revealed several such species over the past few decades. Deeper still, near the seafloor, the environment changes again. Sunlight does not reach these depths at all. The water remains cold and dark year-round. Food becomes scarcer because most organic material must sink from higher levels of the ocean above. Yet even here, life finds ways to persist. The seafloor hosts a variety of animals adapted to scavenging or slow grazing. Sea cucumbers crawl across the sediment searching for edible particles. Brittle stars extend long, flexible arms across the seabed to capture drifting food. Among the strangest inhabitants are sea spiders. Despite their name, these animals are not true spiders. They belong to a separate group of marine arthropods. Many species have extremely long legs compared to their small bodies, giving them an almost delicate appearance. In Arctic waters, some sea spiders grow much larger than their relatives in warmer oceans. Scientists believe this phenomenon may be related to something called polar gigantism. In cold environments, certain marine animals grow larger than similar species elsewhere. Lower temperatures slow metabolism, and high oxygen levels in cold water may allow animals to sustain larger body sizes. The result is a sea floor where familiar creatures appear in unusual proportions. Amphipods that resemble oversized shrimp may grow large enough to fill the palm of a hand. Isopods related to common woodlice become bulky armoured scavengers, moving slowly across the sediment. Some of these animals have been discovered only recently, captured by deep-sea cameras or retrieved in specialized sampling equipment. Another important part of Arctic marine life involves mammals that depend on breathing holes in the ice. Seals are among the most recognizable examples. Ringed seals spend much of their lives beneath sea ice, surfacing periodically through small holes they maintain in the frozen surface. These breathing holes allow seals to access the air while remaining protected from predators above. Polar bears sometimes locate these holes and wait patiently nearby. A bear may remain still for hours, listening for the faint sound of a seal approaching from below. If the seal surfaces in the wrong place at the wrong moment, the bear strikes. It is a dramatic reminder that even in one of the quietest environments on Earth, life involves constant interaction between predator and prey. Whales also travel beneath Arctic ice. Bowhead whales are particularly well adapted to this environment. Their thick layers of blubber help insulate them against freezing water. Some individuals grow more than 18 meters long and may live over 200 years. Bowhead whales use powerful heads to break through thin sea ice when necessary. They navigate beneath the ice using sound, producing complex calls that echo through the ocean. Those calls travel long distances in cold water. Scientists studying Arctic acoustics sometimes record whale songs moving through the dark ocean beneath the ice sheet. Listening to those recordings offers a rare glimpse into an underwater world otherwise hidden from human sight. And whales are not the only large animals moving quietly through Arctic waters. Narwhals, famous for their long spiral tusks, also inhabit the region. The tusk is actually an elongated tooth that can grow more than 2 meters long. Researchers believe it may function as a sensory organ capable of detecting subtle changes in the environment. Narwhals often travel in small groups beneath ice-covered seas, diving deep to hunt fish and squid. Beluga whales, smaller but highly vocal, also frequent Arctic waters. Their bright white bodies stand out against the dark ocean, earning them the nickname sea canaries, because of the wide variety of sounds they produce. Each of these species interacts with the under-ice ecosystem in different ways. Fish feed on smaller crustaceans, seals hunt fish, whales dive deeper for squid or other prey. Organic material from these animals eventually sinks toward the seafloor where scavengers continue the cycle. It is a system built on patience and efficiency. Food is not always plentiful in cold environments, so many Arctic animals have evolved to store energy or survive long periods with minimal feeding. Some species reproduce slowly, but live longer lives. Others migrate seasonally, following shifting ice patterns and currents that influence where food becomes available. And even after centuries of Arctic exploration, scientists still discover new species in these waters. Remote-operated vehicles sent beneath ice shells sometimes capture images of unfamiliar animals drifting through the darkness. Genetic analysis of collected samples occasionally reveals organisms that do not match any previously known species. These discoveries remind researchers that the Arctic Ocean remains one of the least studied marine environments on the planet. The surface of the North Pole may appear quiet and empty, but beneath that frozen ceiling exists a living ocean where microscopic algae cling to the ice. Small crustaceans graze in dim light, fish glide through cold currents, and larger animals navigate a world hidden from human eyes. And as researchers continue exploring deeper into that environment, they have begun encountering creatures that survive in even more unusual conditions, places where sunlight never reaches and where life depends on entirely different sources of energy. If someone could stand beneath the Arctic ice and look upward through the dark water, the frozen ceiling above might appear like a dim grey sky. In certain seasons, faint light filters through snow and ice, creating a hazy glow that slowly fades with depth. But descend far enough, and even that weak illumination disappears. Below a certain point, the Arctic Ocean becomes completely dark. Not the soft darkness of night on land, where moonlight or distant stars still provide some glow. This is a deeper kind of darkness, where sunlight never arrives at all. The water absorbs every trace of it long before reaching the ocean floor. Yet even in that permanent night, life continues. The creatures living in these depths do not rely on sunlight in the way plants and many animals on land do. Instead, they depend on food drifting down from above, on chemical energy released from the seafloor, or on hunting other animals moving quietly through the cold water. The deeper you travel into the Arctic Ocean, the stranger many of these creatures begin to appear. Part of that strangeness comes from the simple fact that sunlight never shaped their evolution. In shallow seas and along coastlines, animals often develop colours, patterns, and visual camouflage. In total darkness, those traits become unnecessary. Colour loses meaning when no light exists to reveal it. As a result, many deep Arctic creatures are pale, translucent, or ghostly white. Their bodies often look delicate and fragile, though they are perfectly suited for the conditions around them. Some fish living in these depths have reduced eyesight, or eyes adapted to detect only the faintest glimmers of light. Others rely more heavily on senses that do not depend on vision at all. One such adaptation involves detecting vibrations. Water carries sound and motion efficiently, so many deep-sea animals sense tiny movements in their environment. Specialized organs along their bodies allow them to detect disturbances created by swimming prey or approaching predators. In darkness, feeling the water becomes as important as seeing it. Some fish in the Arctic depths also possess slow metabolisms. Cold temperatures naturally slow chemical reactions inside living cells, which means animals require less energy to survive. Instead of moving quickly or chasing prey over long distances, many species drift patiently through the water, conserving energy whenever possible. Their lives move at a slower pace, but slow does not mean inactive. In fact, the deep Arctic Ocean hosts a variety of predators that hunt efficiently in complete darkness. Among them are certain species of deep water fish equipped with sensitive lateral lines that detect subtle pressure waves. When a small crustacean or drifting organism moves nearby, the predator senses the disturbance and adjusts its position. The strike itself may take only a fraction of a second. Some species also possess bioluminescence, the ability to produce light using chemical reactions inside their bodies. Bioluminescence appears across many parts of the ocean, but in the deep sea it becomes particularly useful. Small flashes of blue or green light can attract prey, confuse predators, or help animals communicate with others of their kind. In Arctic waters, bioluminescent creatures sometimes drift through the darkness, like faint underwater lanterns. Comb jellies are one example. These delicate animals move using rows of tiny cilia that reflect light in shimmering patterns when illuminated. In complete darkness, some species emit their own faint glow when disturbed. The effect can be subtle, a gentle ripple of light moving across a transparent body before fading again into the black water. Other animals use bioluminescence more strategically. Certain deep-sea shrimp release glowing clouds of chemicals when threatened, creating a brief flash of light that distracts predators while the shrimp escapes into the surrounding darkness. Fish sometimes possess small light-producing organs near their mouths or along their bodies. These lights can attract curious prey or allow individuals to recognize others of the same species. Even bacteria participate in this quiet illumination. Colonies of glowing microorganisms sometimes live inside specialized organs within larger animals, forming partnerships that benefit both organisms. But not all deep Arctic creatures glow. Many rely on patience rather than light. The seafloor beneath the Arctic Ocean is a place of slow movement and careful energy use. Organic material from the upper ocean sinks gradually toward the bottom. Dead plankton, fragments of algae, and other microscopic debris settle into the sediment like falling snow. Scientists sometimes refer to this slow rain of particles as marine snow. For animals living on the seafloor, marine snow provides an important food source. Sea cucumbers move across the sediment collecting these particles. Their bodies resemble soft, elongated tubes with small feeding tentacles surrounding their mouths. As they crawl slowly along the seabed, they gather organic material from the sediment and digest the nutrients inside it. Brittle stars use a slightly different approach. These animals resemble starfish but possess long, flexible arms that extend outward from a small central body. By raising their arms into the water above the seafloor, brittle stars capture drifting food particles or tiny animals carried by currents. When something edible touches their arms, the brittle star quickly moves it toward its mouth. Another unusual group of animals living in deep Arctic waters are polychaete worms. These marine worms vary widely in appearance. Some have smooth cylindrical bodies, while others display rows of small bristles or feathery appendages along their sides. Certain species build protective tubes from sediment, extending their feeding structures into the water to filter small particles. Others move freely across the seafloor searching for food. Because sunlight never reaches these depths, many polychaete worms rely heavily on chemical cues to locate prey or potential mates. Subtle traces of scent carried through the water guide their movements. In the darkness of the Arctic basin, chemical signals become a language of survival. The deeper regions of the Arctic Ocean also host amphipods much larger than those found near the ice surface. Some species reach several centimeters in length and possess strong legs designed for crawling across sediment or swimming slowly through open water. These amphipods act as scavengers. When larger animals die and sink to the ocean floor, amphipods often gather quickly to feed on the remains. Their presence helps recycle nutrients back into the ecosystem. In environments where food arrives unpredictably, scavengers play an essential role. Sea spiders also roam these depths. Their bodies appear almost skeletal at first glance, with extremely long legs extending outward from a small central body. Despite the delicate appearance, sea spiders are capable predators that feed on soft-bodied animals such as hydroids and small invertebrates. Some species possess legs that span surprisingly wide distances relative to their body size, allowing them to move carefully across uneven terrain. Because oxygen dissolves easily in cold water, These animals can absorb enough oxygen directly through their bodies without needing complex respiratory organs. That efficiency helps support their unusual shapes. Occasionally, researchers exploring deep Arctic waters encounter animals that appear unfamiliar even to experienced scientists. Cameras lowered into the darkness sometimes reveal gelatinous organisms with unusual structures or movements. In other cases, samples collected from the seafloor contain small creatures that do not match any known species. Identifying such discoveries requires careful analysis. Researchers examine physical characteristics, compare genetic material, and study how the organism interacts with its environment. Sometimes the process leads to the description of an entirely new species. Other times, the animal turns out to be a rare member of a group already known but poorly studied. Either way, the discovery adds another piece to the puzzle of Arctic biodiversity. Perhaps the most remarkable aspect of these deep ecosystems is their resilience. Life in permanent darkness requires organisms to survive with limited resources. Food may arrive sporadically. Temperatures remain near freezing year-round. Pressure increases dramatically with depth, placing additional stress on biological systems. Yet evolution has produced species capable of thriving under these conditions. Their bodies operate slowly but efficiently. Energy is conserved whenever possible. Adaptations such as antifreeze proteins, pressure-resistant cell structures, and sensitive chemical detection systems allow them to navigate an environment that would seem hostile to most life. For millions of years, these creatures lived beneath the Arctic ice without human observation. Even today, large portions of the deep Arctic Ocean remain unexplored. The darkness that shapes these ecosystems also hides them from easy study. Robotic vehicles and deep-sea cameras provide glimpses, but many areas have never been directly observed. It is entirely possible that species still exist in these depths that scientists have not yet encountered. Creatures moving quietly through water older than human civilization. Animals that evolved in isolation beneath drifting ice, following rhythms of survival far removed from the surface world. And as researchers continue exploring deeper into the Arctic basin, they occasionally discover organisms so unusual that they challenge existing ideas about what kinds of life can survive in such extreme environments. For much of human history, the Arctic Ocean remained an enormous blank space in scientific knowledge. Ships crossed parts of it, explorers walked across drifting ice, and coastal communities hunted along its edges, but the deeper waters beneath the frozen surface stayed hidden for centuries. Even as technology improved, the Arctic proved stubbornly difficult to study. Thick sea ice blocked many research vessels. Storms could arrive quickly and shut down operations for days. Equipment designed for warmer oceans often struggled to function in temperatures hovering near freezing. As a result, scientists only began exploring the deeper Arctic ecosystem in detail during the last few decades. And what they have discovered so far suggests that the ocean beneath the ice still holds many surprises. In the late 20th century, researchers started sending remotely operated vehicles, or ROVs, beneath the Arctic ice. These robotic machines are equipped with cameras, lights, and mechanical arms that allow scientists to observe and collect samples from places too dangerous for human divers. When the first ROVs descended into the dark water under the polar ice, the expectation was modest. Researchers hoped to confirm the presence of known Arctic species and gather better information about the seafloor. Instead, the cameras revealed animals that had never been recorded before. Some appeared delicate and nearly invisible in the water, with gelatinous bodies that glowed faintly when disturbed. Others crawled slowly across the seabed, shaped in ways that looked unfamiliar even to experienced marine biologists. Many of these animals had likely lived in the Arctic Ocean for millions of years. Humans simply had not been able to reach them. One group that attracted particular interest was a type of deep-sea amphipod discovered during Arctic seabed surveys. Amphipods are small crustaceans related to shrimp. but certain deep Arctic species grow far larger than expected. Some individuals measured several centimetres long, with thick bodies and strong legs designed for scavenging across the ocean floor. Researchers studying these amphipods found that they were highly efficient recyclers of organic material. When a fish or other animal died and sank into deep water, amphipods could gather quickly and begin feeding. Their presence ensured that nutrients from dead organisms returned to the ecosystem, rather than remaining locked inside decaying bodies. Although amphipods themselves were already known to science, these particular Arctic species had never been documented before. Another discovery involved unusual types of sea cucumbers living on the deep Arctic sea floor. Sea cucumbers resemble soft, elongated tubes with feeding structures surrounding their mouths. They move slowly across sediment, consuming organic particles deposited from above. During Arctic expeditions using advanced submersible cameras, researchers observed several previously unknown species of sea cucumbers drifting gently above the seabed rather than crawling along it. Instead of remaining on the bottom like typical sea cucumbers, these animals floated slowly through the water using thin appendages that functioned almost like wings. Scientists later identified some of these animals as belonging to a group sometimes called sea pigs. Despite the name, they bear little resemblance to pigs. Their rounded bodies and stubby legs simply reminded early researchers of small piglets wandering across the ocean floor. Sea pigs had been observed in other oceans before, but Arctic surveys revealed species that were new to science. The discoveries did not stop there. In several Arctic expeditions, researchers lowered baited cameras to the seafloor to see which animals might gather around food sources. The results were often surprising. Along with amphipods and sea cucumbers, the cameras captured images of strange worm-like creatures extending feathery feeding structures into the water. These organisms belonged to groups of polychaete worms that had never been recorded in the Arctic basin before. Some species built delicate tubes from sediment, while others moved freely across the seafloor in search of food. Genetic analysis of collected samples revealed that several of these worms represented entirely new species. In fact, the Arctic Ocean has proven particularly rich in previously undocumented polychaetes. The cold environment and isolation created by sea ice allowed many lineages to evolve in relative separation from other ocean ecosystems. Each new expedition adds a few more names to the growing list of Arctic worm species. One of the most visually striking discoveries involved unusual jelly-like animals drifting through the water column beneath the ice. These creatures belong to groups of gelatinous zooplankton that are notoriously difficult to study. Their bodies consist mostly of water and soft tissue, which means they are easily damaged when captured in traditional nets. For many years, scientists suspected that gelatinous animals were common in Arctic waters, but had little direct evidence. High-resolution cameras changed that. ROVs, equipped with sensitive imaging systems, began recording comb jellies, siphonophores, and other gelatinous organisms moving slowly through the dark water. Some of these animals possessed long trailing tentacles used to capture prey. Others pulsed rhythmically as they drifted along ocean currents. Several species observed during these missions had never been described in scientific literature. Because gelatinous animals often look similar at first glance, confirming a new species requires careful examination of body structure and genetic material. Even today, researchers continue to analyze samples from Arctic expeditions, occasionally realizing that a specimen collected years earlier represents a species previously unknown to science. Another remarkable discovery came from studies of microbial life beneath the ice. While large animals capture most public attention, microscopic organisms form the true foundation of marine ecosystems. In the Arctic, researchers discovered entire communities of bacteria and single-celled organisms living in places once thought too extreme for life. Some of these microbes thrive in brine channels within the ice itself. As seawater freezes, salt becomes concentrated in tiny pockets of liquid trapped inside the ice. These narrow channels contain extremely salty water, at temperatures well below the freezing point of ordinary seawater. Yet certain microorganisms survive and even flourish there. These bacteria and algae help support small crustaceans grazing along the underside of the ice. Without them, much of the Arctic food chain would struggle to exist. In other areas of the Arctic Ocean, scientists have identified microbial communities living near hydrothermal vents. Hydrothermal vents are underwater openings where heated water rich in minerals flows upward from deep within Earth's crust. These vents create localized environments where chemical energy replaces sunlight as the primary fuel for life. Bacteria near the vents use chemical reactions to produce energy, forming the base of unique ecosystems that include specialized worms, crustaceans, and other organisms. Although hydrothermal vent communities had been discovered earlier in other oceans, finding them in the Arctic was a significant moment. The Arctic Ridge system contains several vent fields that remain only partially explored. Each one may host species found nowhere else on Earth. In recent years, researchers have also documented new species of fish inhabiting deeper Arctic waters. Some of these fish display remarkable physiological adaptations to cold environments. Antifreeze proteins circulate in their blood, preventing ice crystals from forming in body tissues. Others possess enlarged sensory organs that help them detect movement in the dark. During one deep-sea expedition, scientists recorded a small fish species swimming close to the seafloor at depths rarely studied before in the Arctic basin. Careful analysis revealed subtle differences in body structure and genetic markers compared to known fish species. Eventually, the specimen was recognized as representing a previously undocumented species. Moments like these highlight how much remains to be learned about the Arctic Ocean. Every new tool used to explore beneath the ice reveals animals that had simply escaped observation before. In many cases, the creatures themselves were not particularly rare. They had lived quietly in the Arctic for thousands or even millions of years. What changed was human ability to reach their environment. Modern research vessels equipped with ice-breaking hulls can travel farther into the Arctic than earlier ships. Satellites provide better maps of sea ice movement, allowing scientists to plan expeditions more safely. Autonomous underwater vehicles now explore beneath ice shells without requiring constant human control. Each technological improvement opens new windows into the hidden ocean below, and with each new window comes another discovery. Sometimes it is a strange jelly drifting through cold water. Sometimes it is a worm crawling across sediment where no camera had ever looked before. Sometimes it is a microscopic bacterium living inside salty pockets of ice. Taken together, these discoveries reveal something important about the Arctic. It is not a frozen desert. It is a living ocean system that remained hidden for centuries simply because humans lacked the tools to observe it properly. Even now, scientists estimate that a significant portion of Arctic marine biodiversity remains undocumented. Large areas of the seafloor have never been surveyed in detail. New species may still be drifting through dark water beneath the ice at this very moment, following ancient survival patterns that developed long before the first explorers ventured north. And as researchers continue investigating these hidden ecosystems, they have begun to realize that the Arctic is not only home to newly discovered animals, but also to entire ecological systems that function in ways very different from those found in warmer oceans. At first glance, the Arctic Ocean seems simple. A layer of ice floats on cold water, and beneath that water live a few hardy animals adapted to freezing conditions. That explanation appears reasonable until scientists begin examining the details. When researchers started exploring beneath the ice more carefully, they discovered that the Arctic functions less like a quiet frozen sea, and more like a layered ecosystem, with multiple environments stacked one above another. Each layer supports different forms of life, and each depends on the others in subtle ways. What makes this ecosystem unusual is where it begins. In most oceans, life starts with sunlight reaching open water. Tiny plants known as phytoplankton float near the surface and use sunlight to produce energy through photosynthesis. Those microscopic plants then feed small animals, which in turn feed larger predators. The Arctic, however, spends much of the year covered in ice thick enough to block most sunlight. So the first question scientists asked was simple. How does life begin in a place where sunlight struggles to reach the water? The answer lies in the underside of the ice itself. Although sea ice appears solid from above, its lower surface contains a complex structure of ridges, channels, and tiny pockets where seawater remains trapped. These narrow spaces allow microorganisms to survive inside the ice. When the long Arctic winter begins to fade and sunlight slowly returns to the sky, faint light penetrates through the ice. It may not seem like much, but it is enough to awaken microscopic algae that cling to the ice's underside. These algae grow in thin green layers that stretch across large areas beneath the ice. From the surface, a traveller standing on the frozen ocean would never see them. Yet they form the beginning of a surprisingly productive food web. Small crustaceans gather beneath the ice to graze on these algae. Amphipods and copepods cling to the frozen surface, feeding on the microscopic plants like tiny underwater livestock. Their presence attracts fish. Arctic cod often swim close to the ice, moving slowly through the dim water while feeding on these small crustaceans. The cod themselves become prey for seals and whales, which rely heavily on the seasonal productivity of the ice ecosystem. The entire system begins with a film of life so thin it can be measured in millimeters. But the strange part of the Arctic ecosystem is that it does not exist in just one layer. Below the ice community lies another environment shaped by drifting particles known as marine snow. Marine snow is not actually snow. The name refers to tiny fragments of organic material that slowly sink through the ocean water. Dead plankton, fragments of algae, waste products from animals and other microscopic debris fall from the upper layers toward the sea floor. In warmer oceans, marine snow sinks quickly through open water. In the Arctic, however, the ice cover slows many processes and alters how nutrients move through the system. Some particles become trapped beneath the ice for a time, circulating through currents before finally drifting downward. Others gather along the edges of ice floes where melting creates small zones of open water. This gradual movement of organic material feeds a wide variety of animals living deeper in the ocean. Some creatures wait patiently in mid-water zones, intercepting food before it reaches the seafloor. Others live directly on the bottom, collecting whatever settles into the sediment. Because the Arctic Ocean is relatively enclosed compared to other oceans, its nutrient cycles can behave differently. Water flowing from the Atlantic brings new nutrients into the basin. Pacific water entering through the Bering Strait adds another source of organic material. These currents mix with local biological processes to create a complicated network of energy movement. In some areas, the ecosystem becomes even stranger. Researchers exploring Arctic seafloor ridges discovered regions where chemical reactions provide energy for life instead of sunlight. These areas are associated with hydrothermal vents. Hydrothermal vents form when seawater seeps into cracks in Earth's crust and becomes heated by underlying volcanic activity. The heated water then rises back into the ocean carrying dissolved minerals. When this mineral-rich water meets cold seawater, chemical reactions occur that release energy. Certain bacteria are able to use that chemical energy to produce organic material, much like plants use sunlight in photosynthesis. This process is called chemosynthesis. Around hydrothermal vents, entire ecosystems form based on these bacteria. Worms, crustaceans, and other animals feed on the bacteria or on each other, creating a food chain that operates independently of sunlight. While vent ecosystems are well known in other oceans, their discovery in the Arctic surprised many researchers. The Arctic ridge system contains several vent fields that support unusual communities of organisms adapted to extreme conditions. Here, in total darkness beneath kilometers of water and meters of ice, life continues without any connection to the sun. Another unusual feature of the Arctic ecosystem involves seasonal rhythms. Because the region experiences months of darkness followed by months of continuous daylight, biological activity occurs in pulses. During winter, when sunlight disappears completely, photosynthesis stops. Many organisms reduce their activity and rely on stored energy reserves. Copepods, for example, accumulate large amounts of fat during productive summer months. When winter arrives, they descend deeper into the water column and enter a state similar to dormancy. Fish and other animals continue feeding when possible, but overall biological activity slows. Then spring arrives. Sunlight begins to return to the Arctic sky, and algae beneath the ice start growing again. Within a short time, the ecosystem becomes active. Plankton populations increase rapidly. Fish move toward feeding areas beneath thinning ice. Seals and whales follow prey movements across the ocean. The Arctic ecosystem essentially awakens after months of quiet. This rapid seasonal change is one reason many animals migrate through Arctic waters. Some species travel enormous distances to take advantage of the short but productive Arctic summer. Bowhead whales, for example, follow shifting ice edges and feeding grounds where plankton and small animals gather. Beluga whales travel along coastal regions and under ice-covered seas in search of fish. Seabirds arrive from distant continents to feed in open water areas created by melting ice. For a few months each year, the Arctic becomes one of the most productive marine environments in the world. Then the ice returns, but the ice itself remains an essential part of the ecosystem. Sea ice is not simply a barrier covering the ocean. It acts as a habitat for many organisms. Tiny algae grow within brine channels inside the ice. Crustaceans cling to the underside. Fish shelter in the shadowed water beneath it. Seals depend on the ice for resting, breeding, and raising their young. Polar bears rely on it as a platform for hunting. Without sea ice, the structure of the entire ecosystem changes. Scientists studying Arctic ecology have come to understand that the frozen surface functions almost like a floating continent, supporting its own community of life. The underside of the ice hosts microorganisms. The water beneath supports fish and drifting animals. The seafloor houses scavengers and slow-moving predators. And the ice surface itself provides hunting grounds for mammals and birds. It is a vertical ecosystem stretching from sky to seabed. Another interesting aspect involves how animals navigate the darkness and shifting ice. Sound plays an important role in Arctic waters. Whales communicate across long distances using complex vocalizations. Seals produce calls that travel through water and ice. Some fish generate faint sounds when interacting with others of their species. Hydrophones placed beneath Arctic ice sometimes record a surprisingly active acoustic environment. Clicks, pulses, whistles, and distant echoes move through the water like an underwater conversation. Many of these sounds are still being studied. Some belong to known animals. Others remain uncertain, perhaps produced by species that scientists rarely encounter directly. Because visibility beneath the ice is limited, listening to the ocean has become an important research method. Sound reveals movement where cameras cannot easily reach. Taken together, all of these elements form one of the most unusual ecosystems on Earth. Life begins with microscopic algae growing in dim light beneath ice. Energy flows through crustaceans, fish, seals, and whales. Organic material drifts slowly toward the seafloor where scavengers and bottom dwellers continue the cycle. In certain places, chemical reactions provide energy entirely separate from sunlight. And throughout the system, animals navigate darkness using senses adapted to a world where vision often matters less than vibration, scent, or sound. For centuries, this ecosystem remained largely hidden, simply because humans could not easily see it. The Arctic appeared silent and empty from above, yet beneath that quiet surface, countless interactions were unfolding every day. Fish hunting in shadowed water, crustaceans grazing along the ice, whales moving through narrow corridors beneath drifting floes, and occasionally in the deep darkness of the Arctic basin, scientists have encountered environments so unusual that they seem almost like separate worlds within the ocean itself. Far below the drifting ice of the Arctic Ocean, beyond the reach of sunlight and far beneath the slow movements of fish and whales, the sea floor is not always the quiet place people imagine. In certain areas, the ground itself opens into narrow cracks where heat escapes from deep inside the planet. These places are known as hydrothermal vents, and they form one of the most unusual environments anywhere in the Arctic. The word hydrothermal simply describes water that has been heated underground. Seawater seeps through fractures in the ocean crust and travels downward into regions where the rock is warmed by magma deep below. As the water heats up, it dissolves minerals from the surrounding rock. Eventually, that hot, mineral-rich water rises back toward the surface and escapes through vents on the seafloor. When it meets the surrounding ocean, the change in temperature is dramatic. Water leaving a hydrothermal vent can reach temperatures of several hundred degrees Celsius, though the intense pressure at those depths prevents it from boiling. The surrounding Arctic seawater, meanwhile, sits only a few degrees above freezing. Where these two environments meet, strange towers of mineral deposits begin to grow. These formations are sometimes called chimneys. They build slowly as dissolved minerals in the vent water cool and solidify when they mix with the cold ocean. Over time, the chimneys can rise several meters above the seafloor, forming dark structures that release cloudy plumes into the surrounding water. For many years, scientists assumed that environments like this would be lifeless. The deep ocean lacks sunlight, and temperatures near vents fluctuate dramatically. In addition, the water emerging from these openings contains chemicals that would be toxic in most other environments. Yet when the first deep-sea expeditions discovered hydrothermal vents in other oceans during the late 20th century, they also found something unexpected. Entire ecosystems existed around them. Instead of relying on sunlight as the base of the food chain, these ecosystems depended on chemical energy released from the Earth itself. Bacteria living near the vents could use chemicals such as hydrogen sulfide to produce organic matter through a process known as chemosynthesis. In simple terms, these bacteria performed a role similar to plants in sunlit environments, but their energy came from chemical reactions rather than light. Once scientists realized this process was possible, they began searching for similar ecosystems in other parts of the ocean. Eventually, attention turned toward the Arctic. The Arctic Ocean contains several underwater mountain ranges and spreading ridges where tectonic plates slowly move apart. One of these systems, known as the Gackel Ridge, stretches across the deep Arctic basin. Because the ridge lies beneath thick sea ice for most of the year, exploring it remained extremely difficult for decades. Research ships could not easily reach the area. Submersible vehicles had limited operating ranges. Even locating potential vent sites required careful sonar mapping of the seafloor. But eventually scientists began to detect hints that hydrothermal activity might exist there. Certain chemical signals appeared in water samples collected above the ridge. These signals suggested that mineral-rich fluids were entering the ocean from below. In 2001, a major expedition set out to investigate. Using ice-breaking research vessels and deep-sea instruments, scientists surveyed the ridge system beneath the Arctic ice. After careful mapping, they lowered cameras and sensors toward the seafloor. What they discovered confirmed their suspicions. Hydrothermal vents were indeed active along the ridge. Dark plumes of mineral-rich water rose slowly from chimney-like formations scattered across the seafloor. Temperatures near the vents were dramatically higher than the surrounding water, and most importantly, life had gathered around these openings. Clusters of unusual animals surrounded the vent structures. Some species resembled organisms found at hydrothermal vents in other oceans, while others appeared distinct enough to represent entirely new branches of deep-sea life. Among the most noticeable residents were specialized shrimp-like crustaceans that crawled across the mineral surfaces. These animals appeared to feed on bacterial mats growing near the vents. Their bodies were adapted to withstand high temperatures and chemical conditions that would harm most marine species. Certain worms also inhabited the area. Although they looked somewhat similar to polychaete worms found elsewhere on the seafloor, the vent-dwelling species displayed adaptations suited to life near hydrothermal activity. Some possessed feathery appendages used to gather bacteria and organic particles from the water. Others formed symbiotic relationships with chemosynthetic bacteria living within their tissues. In such partnerships, the bacteria produced nutrients through chemical reactions, while the host organism provided protection and access to the chemicals needed for energy production. This arrangement allowed animals to survive in places where traditional food sources were scarce. Another interesting feature of Arctic hydrothermal vents involves the microbial communities that form the base of the ecosystem. Bacteria colonize the surfaces of vent chimneys and surrounding rocks. Some species grow in thick layers that appear almost like carpets covering the mineral structures. These bacterial colonies process chemicals released from the vents and convert them into organic material that other organisms can consume. In effect, they serve the same ecological role that plants perform in forests or grasslands. Without them, the entire ecosystem would collapse. The Arctic vent systems differ from those in warmer oceans in several important ways. Because the surrounding seawater is extremely cold, temperature gradients near the vents are particularly sharp. Just a short distance from the vent opening, water temperatures drop rapidly toward near-freezing conditions. Organisms living in this environment must tolerate dramatic shifts in temperature, depending on how close they remain to the vent. In addition, the Arctic vents exist beneath thick sea ice that restricts sunlight and alters ocean circulation patterns. Nutrient transport behaves differently compared to open ocean environments. As a result, the ecosystem surrounding Arctic vents may evolve in relative isolation. Some scientists believe this isolation has allowed unique species to develop over long periods without mixing extensively with populations in other oceans. In other words, these vents may host life found nowhere else on Earth. Another challenge for vent-dwelling animals involves pressure. The deep Arctic basin reaches depths of several thousand meters. At those depths, water pressure becomes immense. Organisms living there must possess cellular structures capable of functioning under these conditions. Their enzymes and biological membranes operate differently than those of shallow water species. Temperature, pressure, chemical exposure and darkness combine to create one of the most demanding habitats on the planet. Yet life persists there. Researchers studying Arctic hydrothermal vents often describe the experience of watching video recordings from submersible cameras. In the glow of artificial lights, mineral chimneys appear like strange towers rising from the sea floor. Clouds of dark fluid drift upward into the water above, and moving slowly around these formations are animals that seem almost unaware of the harsh environment surrounding them. Shrimp-like crustaceans crawl across rocks. Worms extend their feeding appendages into the currents. Small fish occasionally swim past, investigating the unusual warmth near the vent. It is a scene that feels both alien and familiar at the same time. Alien because of the extreme conditions and unusual shapes of many organisms. Familiar because the basic ecological relationships still exist. Something produces energy. Something consumes that energy. Predators and scavengers appear to take advantage of the resulting food chain. One important difference between vent ecosystems and typical Arctic marine environments involves stability. Sea ice ecosystems change dramatically with the seasons. During winter darkness, biological activity slows. When sunlight returns in spring, productivity increases rapidly. Hydrothermal vents operate on a different rhythm. As long as geological activity continues beneath the seafloor, the vents remain active year-round. Chemical energy flows steadily from the Earth's crust into the surrounding water. This means vent ecosystems can remain productive even during the long Arctic winter when surface waters grow quiet. However, hydrothermal vents are not permanent. Over time, mineral deposits may block vent openings, or geological activity may shift to new locations along the ridge. When that happens, the local ecosystem must either adapt or disappear. Some animals migrate to nearby vents, others may die out if suitable habitat cannot be found. The process resembles a slow-moving cycle of creation and decline taking place deep beneath the ocean. Despite their scientific importance, Arctic hydrothermal vents remain difficult to study. The combination of thick ice cover, deep water, and harsh weather limits how often research teams can visit these sites. Many vent fields have been observed only a few times. Large portions of the Arctic ridge system remain unexplored. This means additional vent ecosystems may still exist in areas no submersible has yet reached. Each potential discovery could reveal new species, new microbial communities, and new insights into how life adapts to extreme conditions. Studying these environments also helps scientists understand broader questions about life on Earth. If organisms can thrive using chemical energy alone in complete darkness, beneath kilometers of water and ice, similar forms of life might exist in other places in the solar system. Some researchers consider hydrothermal vents a possible model for environments beneath the icy surfaces of moons such as Europa or Enceladus, where hidden oceans may interact with warm rocky interiors. In that sense, the strange ecosystems beneath Arctic ice may offer clues about life far beyond our planet. For now, though, they remain one of the many secrets hidden beneath the frozen roof of the Arctic Ocean. While explorers once focused only on reaching the surface of the North Pole, modern science has revealed that entire communities of organisms live quietly in the darkness far below, and even beyond the vents, deeper regions of the Arctic basin still hold environments that scientists have only just begun to explore. If someone were to collect a single cup of water from the Arctic Ocean and examine it carefully under a microscope, the number of living organisms inside that small sample would likely be surprising. Even in water that appears perfectly clear, thousands of microscopic creatures move slowly through the currents, drifting, feeding, and reproducing in ways that shape the entire Arctic ecosystem. When people imagine life in the Arctic, they often picture large animals first. Polar bears walking across sea ice, seals surfacing through breathing holes, or whales travelling beneath the frozen surface. These animals are certainly important parts of the Arctic environment, but they represent only the most visible pieces of a much larger system. In truth, the Arctic Ocean is governed largely by organisms so small they cannot be seen without magnification. These microscopic creatures form the base of nearly every food chain in the region. Without them, fish, seabirds, and marine mammals would struggle to survive, and yet for centuries their presence went almost entirely unnoticed. The story begins with microscopic plants known as phytoplankton. Phytoplankton are single-celled organisms capable of photosynthesis. Using sunlight and dissolved nutrients in seawater, they produce organic material that becomes the starting point for marine food webs. In warmer oceans, phytoplankton bloom in enormous numbers during certain seasons, colouring the water with faint shades of green. The Arctic has long been considered a difficult place for phytoplankton to grow. For much of the year, the ocean is covered by thick ice, which blocks most sunlight from reaching the water. Winter darkness can last several months near the North Pole. During that time, photosynthesis becomes nearly impossible. Yet when sunlight finally returns in spring, something remarkable happens. As the sun climbs slowly above the horizon, light begins filtering through thinning ice and snow. The faint illumination triggers the growth of phytoplankton in the upper layers of the ocean. These organisms reproduce rapidly. Within a short time, the water can fill with billions of microscopic cells, each capturing a small amount of sunlight and converting it into energy. The result is known as a phytoplankton bloom. Although the bloom may last only a few weeks or months, it provides enough food to support much of the Arctic marine ecosystem for the entire year. Researchers studying satellite images of Arctic waters sometimes observe subtle colour changes indicating these blooms. Beneath the ice, however, many blooms remain hidden from view. Only careful sampling reveals the scale of this activity. Phytoplankton are not the only microscopic organisms involved in this system. Alongside them drift tiny animals known as zooplankton. Zooplankton include a wide variety of small creatures such as copepods, larval fish, jellyfish embryos, and other minute organisms that feed on phytoplankton or even smaller microbes. Among the most important members of this group in the Arctic are copepods. Copepods resemble tiny shrimp, often measuring only a few millimeters long. Despite their small size, they exist in astonishing numbers. In some regions of the Arctic Ocean, copepods may outnumber larger animals by millions to one. They graze continuously on phytoplankton during the productive summer months. But copepods possess another unusual adaptation that allows them to survive the long Arctic winter. During times of abundant food, many species store large quantities of fat inside their bodies. These fat reserves allow them to descend deeper into the ocean when winter arrives and remain inactive for months without feeding. In effect, they enter a state similar to hibernation. When spring returns and phytoplankton begin blooming again, the copepods rise back toward the surface to resume feeding. This seasonal cycle plays a crucial role in Arctic food chains. Fish species such as Arctic cod depend heavily on copepods as a food source. In turn, larger predators depend on the fish. Without these tiny animals storing and transferring energy through the ecosystem, many Arctic species would struggle to survive the long winter months. But phytoplankton and zooplankton represent only part of the microscopic community. Bacteria and other microorganisms also play essential roles. Marine bacteria help break down organic material drifting through the ocean. When phytoplankton die or when animals produce waste, bacteria decompose those materials and release nutrients back into the water. These nutrients then become available again for phytoplankton growth. The process forms a recycling system known as the microbial loop. In the Arctic, this loop is particularly important because resources are limited and must be reused efficiently. Cold temperatures slow many biological processes, so decomposition happens gradually. Bacteria ensure that nutrients continue circulating through the ecosystem, even when larger organisms are less active. Some bacteria in Arctic waters have developed unusual biochemical abilities. Certain species produce proteins that protect their cells from freezing temperatures. Others can survive in extremely salty brine channels trapped inside sea ice. As seawater freezes, salt is excluded from the forming ice crystals and becomes concentrated in narrow liquid channels within the ice structure. These channels remain filled with brine, even at temperatures well below the freezing point of ordinary seawater. For most organisms, such conditions would be lethal. Yet specialized bacteria and algae thrive inside these microscopic environments. Within the ice itself, they form tiny ecosystems, feeding on dissolved nutrients and interacting with small crustaceans that move through the brine channels. Scientists studying Arctic sea ice sometimes refer to it as a living habitat rather than a simple frozen barrier. Entire communities exist within the ice matrix. Another fascinating group of microscopic organisms found in the Arctic are protists. Protists are single-celled eukaryotic organisms, meaning their cells contain a nucleus. They include a diverse collection of species that behave in different ways. Some protists function like plants, performing photosynthesis and contributing to phytoplankton blooms. Others behave more like animals, hunting bacteria or smaller protists. Still others combine both strategies depending on environmental conditions. Because protists occupy many different ecological roles, they help stabilize Arctic food webs. When one group declines due to seasonal changes, others may take its place in processing nutrients and energy. Recent advances in genetic sequencing have revealed just how diverse these microscopic communities are. By analyzing DNA fragments in seawater samples, researchers can identify organisms that might otherwise go unnoticed. These studies have uncovered thousands of microbial species living in Arctic waters, many of which have never been formally described. Some belong to lineages rarely found in other parts of the ocean. Others appear uniquely adapted to the cold, low-light environment beneath sea ice. The complexity of these microbial communities surprised many scientists. For years, the Arctic was thought to host relatively simple ecosystems compared to warmer oceans. Instead, it turns out that microscopic diversity beneath the ice rivals that of more familiar marine environments. Another interesting aspect of Arctic microbial life involves viruses. Marine viruses infect bacteria and plankton cells, influencing population sizes and nutrient cycling. When viruses infect microbial cells and cause them to burst, the released contents become available as food for other organisms. Although viruses often carry negative connotations in everyday life, in marine ecosystems they help maintain balance among microbial populations. In the Arctic, viral activity may play an important role in controlling plankton blooms and recycling nutrients. Even the long winter darkness does not completely halt microbial activity. While phytoplankton rely on sunlight and remain mostly inactive during the polar night, many bacteria continue processing organic material throughout the winter months. Some microorganisms even grow slowly using chemical energy or dissolved organic compounds. These processes keep the Arctic ecosystem functioning even when larger animals reduce their activity. Taken together, these microscopic organisms form the true foundation of life in the Arctic Ocean. Phytoplankton capture sunlight when it returns each spring. Zooplankton consume phytoplankton and store energy for later use. Bacteria recycle nutrients from organic debris. Protists fill multiple ecological roles within the microbial community. Viruses regulate populations and contribute to nutrient cycling. Without this invisible network of interactions, the larger animals of the Arctic would have nothing to eat. Fish would struggle to find prey. Seals and whales would find fewer feeding grounds. Even polar bears, standing on the ice above it all, ultimately depend on the productivity of microscopic organisms drifting in the water below. Despite their importance, scientists have only recently begun to understand the full complexity of Arctic microbial ecosystems. Advances in molecular biology and ocean sampling techniques now allow researchers to identify species that cannot be easily observed under a microscope. Each new study reveals additional layers of diversity. Some microorganisms appear to exist only beneath Arctic ice. Others display unusual metabolic processes suited to the cold, nutrient-limited environment. And because the Arctic Ocean is changing as global temperatures rise, scientists are paying closer attention to how these microscopic communities respond. Small shifts in microbial populations could ripple through the entire food web. The Arctic ecosystem may seem dominated by ice, wind, and cold water, but beneath that surface lies a dynamic community of organisms far too small to see. Tiny cells drifting through dark currents, invisible populations multiplying during brief bursts of sunlight, microscopic architects quietly sustaining one of the most unusual marine ecosystems on Earth. And even beyond these hidden microbial worlds, the Arctic Ocean still contains animals that appear surprisingly large and unfamiliar, creatures whose existence few people ever imagine when they picture the frozen sea. When people imagine animals of the Arctic, a few familiar images usually come to mind. A polar bear standing on drifting ice, a seal surfacing through a breathing hole, perhaps a whale moving slowly through cold northern waters. These animals have become symbols of the region, appearing in documentaries, photographs and stories about life near the top of the world. Yet the Arctic Ocean contains other large creatures that rarely receive the same attention. Some live far below the ice where few cameras have travelled. Others inhabit remote areas of the seafloor or deep water layers where direct observation is difficult. In many cases, these animals are not only large but unusual, shaped by conditions that differ greatly from warmer oceans. One of the reasons such creatures exist in Arctic waters involves a phenomenon scientists sometimes call polar gigantism. In cold environments, certain marine species grow larger than their relatives living in warmer seas. Researchers believe several factors contribute to this pattern. Cold water holds more dissolved oxygen, which may allow animals to support larger body sizes. Slower metabolisms also mean that energy is used more gradually, allowing organisms to grow slowly over long lifespans. The result is a collection of Arctic species that appear surprisingly large when compared to their more familiar relatives. Consider the giant Arctic amphipods. Amphipods are small crustaceans related to shrimp. In many parts of the world, they remain only a few millimeters long. In the deep Arctic, however, some species reach several centimeters in length. To someone encountering them for the first time, they look like oversized shrimp or miniature lobsters drifting slowly through the water. These amphipods play an important role in the ecosystem. They are scavengers, feeding on organic material that sinks to the ocean floor. When larger animals die and their bodies descend through the water column, amphipods often gather quickly to feed. Deep-sea cameras lowered to the Arctic seabed sometimes reveal dozens of these creatures surrounding a single food source. Their size and numbers make them effective recyclers of nutrients, ensuring that organic matter returns to the ecosystem rather than remaining trapped in decaying remains. Another group of large but rarely seen Arctic animals includes the giant sea spiders. Despite their name, sea spiders are not true spiders. They belong to a different branch of marine arthropods. Their bodies consist of a small central segment from which extremely long legs extend outward. In some Arctic species, those legs can span distances several times the length of the animal's body. When viewed on camera, these creatures appear almost delicate. Their thin limbs move slowly across the seafloor, while the central body remains small and compact. Yet they are effective predators. Sea spiders feed on soft-bodied animals such as hydroids and small invertebrates. They use specialized mouth parts to pierce their prey and extract nutrients. In colder waters, their bodies can grow larger than those of related species living in warmer environments, another example of polar gigantism in action. Then there are the giant isopods. Isopods belong to a group of crustaceans that includes common woodlice found on land. Most isopods remain small, but certain deep-sea species grow to impressive sizes. Although the largest examples have been found in other oceans, Arctic waters host several unusually large isopod species that move slowly across the seabed. Their bodies are armoured with overlapping plates, giving them a sturdy appearance. When disturbed, they can curl into a protective ball, much like their smaller relatives on land. These animals often act as scavengers, feeding on organic material that settles on the ocean floor. Because food is not always abundant in deep Arctic environments, giant isopods may survive long periods without feeding. Some individuals have been observed going months between meals. Another little-known giant of the Arctic is the Greenland shark. Unlike many other creatures mentioned so far, this animal occasionally appears closer to the surface and has been observed by fishermen and researchers alike. Even so, the Greenland shark remains one of the least understood large predators in the ocean. These sharks can grow more than 6 meters in length, placing them among the largest shark species alive today. Their bodies move slowly through cold Arctic water, often at depths far below where most human activity occurs. One remarkable feature of the Greenland shark is its lifespan. Recent studies suggest that some individuals may live for several centuries. By analysing proteins in the shark's eye tissue, scientists have estimated ages exceeding 400 years for certain specimens. If these estimates are correct, some Greenland sharks swimming in Arctic waters today may have been alive during periods of human history, long before modern exploration reached the polar regions. The sharks move slowly, conserving energy in cold water. Their diet appears varied. They feed on fish, squid, and occasionally marine mammals. Scavenging also plays a role, with sharks consuming carcasses that sink into deeper waters. Despite their large size, encounters between Greenland sharks and humans remain rare. Most observations come from deep-sea cameras or occasional accidental captures during fishing operations. Another giant inhabitant of Arctic waters is the bowhead whale. While whales are not unknown to science, the bowhead deserves special mention because of its unusual adaptations to life beneath Arctic ice. These whales can grow up to 18 meters long and possess thick layers of blubber that protect them from freezing temperatures. Their massive skulls allow them to break through sea ice when necessary. creating breathing holes where none existed before. Bowhead whales feed primarily on zooplankton such as copepods and small crustaceans. Using large baleen plates in their mouths, they filter enormous volumes of water to capture tiny prey. Although their diet consists of microscopic animals, the whales themselves grow to extraordinary sizes. Like the Greenland shark, bowhead whales may live extremely long lives. Some individuals have been estimated to exceed 200 years of age. Occasionally, researchers have discovered fragments of old hunting equipment embedded in the whales' bodies, suggesting they survived encounters with whalers more than a century ago. In deeper Arctic waters, another unusual giant occasionally appears on research cameras, the giant Arctic jellyfish. Certain species of jellyfish in cold northern oceans grow much larger than their relatives in warmer waters. Their bell-shaped bodies may span several meters across, while long tentacles trail far behind them. When illuminated by submersible lights, these jellyfish drift slowly through dark water like pale umbrellas suspended in the ocean. Their tentacles capture small fish and plankton that drift too close. Because gelatinous animals are difficult to collect intact, much about these large jellyfish remains uncertain. Scientists often rely on video observations rather than physical specimens to study them. There are also large Arctic squid species inhabiting deeper waters. Although they are rarely seen, occasional captures by fishing vessels or glimpses on deep-sea cameras confirm their presence. Squid rely on powerful jet propulsion and keen eyesight to hunt in dark water. Their bodies are streamlined, with long arms equipped with suckers that grasp prey quickly. Some squid species may reach lengths of several meters, including their extended arms. The deep Arctic basin provides plenty of space for such animals to move undetected. And then there are the giant sea cucumbers, sometimes called sea pigs. These animals resemble small inflated creatures with stubby legs extending from their undersides. They crawl slowly across the seafloor, collecting organic material from sediment. While not enormous by human standards, certain Arctic species grow larger than similar animals elsewhere. Seen through the lens of a deep-sea camera, groups of sea pigs may appear like wandering herds crossing the dark seabed. Their movements are slow and deliberate. Taken together, these animals reveal that the Arctic Ocean contains not only microscopic life and small crustaceans, but also creatures of considerable size. Some are predators moving quietly through dark water. Others are scavengers cleaning the seafloor. Still others filter enormous quantities of plankton from the ocean. Most remain out of sight simply because their habitat lies beneath thick ice, or at depths rarely visited by research equipment. Human understanding of these species continues to grow slowly as technology improves. Each deep-sea expedition brings new observations. A camera may capture a creature rarely seen before. A sample retrieved from the seafloor may reveal a species larger than expected. Sometimes the discovery leads scientists to realize that the Arctic Ocean hosts far more biological diversity than earlier generations ever imagined. And occasionally researchers encounter something even more puzzling. Animals glimpsed only once, recorded briefly by cameras before disappearing again into the dark waters beneath the ice. In the Arctic, sound behaves differently than it does in most places people are familiar with. On land, noise is quickly absorbed by trees, buildings, soil, and moving air. Even in open landscapes, sound fades gradually as distance increases. In the Arctic, however, the environment changes the way vibrations travel. Ice, water, and cold air create a kind of natural amplifier. A noise made far away can sometimes travel long distances through the frozen landscape. Vibrations pass through solid ice sheets, across the surface of snow, and through the dense water beneath the frozen ocean. Because there are few obstacles to interrupt these vibrations, certain sounds can travel much farther than expected. For explorers and researchers working in the Arctic, this has led to some strange listening experiences. A person standing alone on sea ice might hear low, rumbling noises coming from the distance, even when nothing visible is moving. A faint knocking sound may echo upward through the frozen surface beneath their feet. Occasionally a long, deep tone can travel across the ice, like the slow vibration of a distant bell. Many of these sounds have ordinary explanations once scientists examine them closely. Ice is constantly moving, expanding, and cracking as temperatures change. When large sheets of ice press against one another, the friction produces grinding noises that travel through the frozen surface. In some cases, the sound resembles distant thunder. At other times, it is more like the slow creak of an enormous wooden ship adjusting under pressure. These noises are part of the natural behaviour of sea ice. The frozen ocean is never completely still. Wind pushes the ice, currents pull it from below, and temperature changes cause expansion or contraction. Yet not every sound recorded in the Arctic has been easily explained. As scientific equipment improved during the late 20th century, researchers began placing underwater microphones beneath the ice. These devices, called hydrophones, are capable of detecting extremely faint sounds travelling through water. Hydrophones revealed that the Arctic Ocean is far more acoustically active than anyone had expected. Whales communicate across great distances using low-frequency calls. Beluga whales produce a wide variety of whistles, chirps, and clicking noises. Narwhals generate bursts of sound that bounce off objects in the water, allowing them to navigate and locate prey. All of these sounds form a kind of underwater conversation. When scientists first began recording Arctic waters, they could easily identify many of these signals by comparing them with known whale vocalizations. But occasionally something different appeared in the recordings. Instead of a recognizable pattern of whale calls or ice movements, the hydrophones captured unfamiliar sounds. Some recordings contained slow pulses repeating at regular intervals. Others featured strange metallic tones or rising vibrations that did not match the acoustic patterns of known marine animals. Researchers initially assumed these signals might come from ships or distant human activity, but many recordings were made in extremely remote areas where no vessels were present. One well-known example occurred during acoustic monitoring programs in the Canadian Arctic. For several years, scientists studying marine mammal communication repeatedly detected a low humming sound in their hydrophone recordings. The noise occurred during certain seasons and seemed to originate from deep beneath the ice. Because the sound was relatively simple, resembling a steady hum or drone, researchers struggled to identify its source. Eventually the sound was nicknamed the Arctic hum. Various explanations were proposed. Some scientists suggested that shifting ice might produce the vibration. Others believed it could be related to underwater geological activity such as small earthquakes, or the movement of sediment along the ocean floor. Another possibility involved large groups of fish producing synchronized movements that created acoustic disturbances. Despite these ideas, no single explanation has been confirmed. The sound remains one of several unusual acoustic phenomena recorded beneath Arctic ice. Another puzzling set of recordings involved brief knocking sounds detected by hydrophones placed along certain Arctic coastlines. These knocks occurred irregularly, sometimes repeating several times in quick succession before stopping entirely. They were louder than typical ice cracking noises, but lacked the clear tonal patterns of whale communication. Some researchers wondered whether unknown marine animals might be responsible. Many species of fish produce sound by vibrating specialized muscles connected to their swim bladders. These vibrations can create rhythmic drumming or knocking noises underwater. However, the recorded sounds did not perfectly match known fish acoustics either. Another explanation involved ice interacting with ocean currents. When currents push water through narrow channels beneath sea ice, pressure differences can produce vibrations. These vibrations may travel through the ice sheet and emerge as faint tapping sounds at the surface. Yet again, confirming this theory has proven difficult. Arctic ice conditions vary widely from one location to another, making controlled experiments challenging. Perhaps the most mysterious sounds recorded in the Arctic came from a series of hydrophone recordings in the Beaufort Sea during the early 2010s. Scientists studying whale migration detected an unusual noise that lasted several seconds and had a rising, almost musical quality. The sound began as a low tone before climbing rapidly in pitch, then ending abruptly. Researchers compared the recording with known whale calls, ice noises and mechanical sounds produced by ships or submarines. None matched exactly. Because the sound resembled a strange electronic buzz, some people jokingly referred to it as the Arctic beep. The nickname spread quickly among marine researchers. Theories about the sound included unusual whale vocalizations, shifting ice ridges under pressure, or even mechanical interference from distant industrial activity. Over time, many scientists came to believe the sound was likely produced by a type of whale whose call had not been fully documented before. Even so, the exact source remains uncertain. Part of the difficulty lies in the Arctic environment itself. Recording equipment placed beneath sea ice must endure extreme cold and pressure. Instruments can remain deployed for months before being retrieved. During that time, they capture enormous quantities of acoustic data. Sorting through those recordings takes careful analysis. Researchers must separate natural sounds from mechanical noise, filter out interference from storms, and identify patterns that might correspond to animal communication. Even when a strange sound is clearly detected, locating its exact source is not always possible. Hydrophones record vibrations but do not necessarily reveal where those vibrations originated. If multiple hydrophones capture the same signal, scientists can sometimes triangulate the location. But when only a single instrument records the sound, determining its origin becomes much harder. Ice itself complicates the situation further. The frozen surface reflects and redirects sound waves travelling through the water below. Vibrations may bounce between ice layers, seafloor structures, and underwater ridges before reaching the hydrophone. By the time the sound is recorded, its path may have changed direction several times. Another factor involves the vastness of the Arctic Ocean. Large areas remain sparsely monitored. Hydrophones operate only in specific locations chosen for research projects. If an unusual sound originates far from these sensors, it may never be detected at all. This means the acoustic landscape of the Arctic is only partially understood, and the more scientists listen, the more complex it appears. Some recordings reveal the presence of marine animals previously thought rare in certain regions. Others show how ice itself produces an astonishing variety of sounds depending on weather, temperature, and ocean currents. Occasionally, however, a sound appears that does not fit neatly into existing categories. It may be a new type of whale vocalization. It may result from unusual geological activity beneath the seafloor. It may simply be an acoustic effect created by shifting ice interacting with ocean water in ways not fully studied. For now, some recordings remain unexplained. That does not necessarily mean they are mysterious in the dramatic sense. More often, it reflects the difficulty of studying an environment where direct observation is limited and conditions change constantly. Still, the idea that unfamiliar sounds travel quietly beneath the Arctic ice has captured the imagination of many researchers. In the dark water below, whales communicate across long distances. Ice plates grind together as currents push them slowly across the ocean. Fish, crustaceans, and other animals move through currents that carry vibrations far from their source. All of these sounds blend into a constantly shifting acoustic landscape. Listening to recordings from beneath the ice sometimes feels like hearing a distant conversation carried through a thick wall. Some voices are clear and recognizable, others are faint or unfamiliar, and somewhere within that mixture of echoes, pulses, and vibrations may lie signals from creatures that scientists have rarely seen directly. The Arctic Ocean remains one of the least explored acoustic environments on Earth. Researchers continue placing hydrophones beneath the ice, hoping to understand how animals navigate this frozen world and how the environment itself shapes the sounds moving through it. With each new recording, the picture becomes a little clearer. Yet the deep water beneath the Arctic still holds many mysteries, and occasionally those mysteries appear not as strange shapes caught on camera, but as brief sounds travelling through the cold, dark ocean before fading again into silence. In most parts of the world's oceans, when scientists discover a new species, they usually have an opportunity to observe it more than once. A research vessel might return to the same region several times, nets might collect multiple specimens, and eventually the animal becomes familiar enough to study in detail. The Arctic Ocean does not always allow that kind of repeated observation. Much of the Arctic remains difficult to access. Thick sea ice blocks many routes for ships, and severe weather can close research windows quickly. When scientists lower cameras or instruments into the water beneath the ice, they are often looking into places that no one has observed before. The equipment may remain there only for a short period before being pulled back to the surface. In such circumstances, an animal may appear briefly on camera and then vanish into the surrounding darkness. Sometimes that brief appearance becomes the only record scientists have of that creature. Marine biologists studying Arctic ecosystems have encountered this situation several times. A remotely operated vehicle might be descending slowly through the water column when a strange organism drifts past the camera. It might appear only for a few seconds, illuminated by the vehicle's lights before disappearing beyond the frame. If the researchers are lucky, the video recording captures enough detail to analyse later. But without a physical specimen, identifying the animal can become extremely difficult. One of the most common examples involves gelatinous organisms. Animals such as comb jellies, siphonophores, and certain jellyfish have bodies made mostly of water. Their tissues are delicate and easily damaged when collected in nets. Even when scientists attempt to capture them, the animals may collapse into shapeless fragments before reaching the surface. As a result, some species have been observed only through video footage. In several Arctic expeditions, researchers recorded unfamiliar comb jellies moving through deep water beneath the ice. These animals displayed body shapes or tentacle arrangements that did not match any known species. Their movements were slow and rhythmic, with rows of tiny cilia producing faint shimmering patterns in the artificial light. Yet because no specimen was collected, scientists could only classify them tentatively. The video provided a glimpse, but not a complete understanding. Another situation occurred during deep-sea surveys of Arctic seafloor ridges. A remotely operated vehicle exploring a previously unmapped region recorded a worm-like creature crawling across the sediment. The animal possessed a series of feathery appendages extending from its body, each moving gently as if sensing the surrounding water. Researchers reviewing the footage noticed that the creature's structure differed from known polychaeta worms commonly found in deep oceans. However, the vehicle had already moved past the location before the scientists could adjust its position to collect the specimen. The animal disappeared into the sediment and was never seen again. Without additional observations, confirming whether it represented a new species remains impossible. Similar encounters have occurred with small crustaceans. During one Arctic expedition studying scavengers of the deep basin, a baited camera recorded an unusual amphipod approaching the bait. Its body appeared larger and more heavily armoured than typical amphipods known from the region. For several minutes it circled the bait cautiously before swimming away. Although the recording clearly showed the animal, it was not captured. Later analysis suggested it might belong to a species not previously described in Arctic waters. But without physical samples, researchers could only speculate. In the deep ocean, even a brief appearance can be valuable. Every piece of footage adds to the overall understanding of how life behaves in these environments. Scientists often archive recordings for years, comparing them with later observations in case a similar creature appears again. Occasionally the same species is rediscovered during a later expedition, confirming that the original sighting was not simply an anomaly. Other times the animal remains known only from a single moment of observation. Large animals sometimes appear only once as well. In rare cases, deep-sea cameras have recorded fish species moving slowly across the field of view that do not resemble any documented Arctic fish. These encounters tend to happen at great depths, where few research missions operate regularly. A camera may capture a fish with an unusual body shape or fin structure. But if the animal quickly swims out of view, collecting a specimen becomes impossible. Deep-sea fish can also inhabit extremely wide territories. Even if scientists return to the same location later, the animal may have moved far away. The Arctic environment adds further complications. Ice cover restricts how long research vessels can remain in one area. Weather conditions can force teams to retrieve equipment earlier than planned. Remote vehicles operating beneath the ice must eventually return to a designated opening or launch point before their batteries run low. All of these limitations reduce the chances of observing the same creature repeatedly. Another factor involves the behaviour of the animals themselves. Many deep-sea species are naturally cautious. Bright lights from research equipment may disturb them. Some creatures react by drifting away slowly, while others retreat quickly into darkness. For example, certain squid species detected on Arctic cameras appear only as brief silhouettes before accelerating out of view. Squid possess excellent eyesight even in dim environments. When illuminated suddenly by artificial lights, they often respond by swimming rapidly away from the source. This reaction makes capturing them on video difficult and collecting specimens even harder. Some of the most puzzling sightings involve animals that look unlike anything scientists expected to find in the Arctic. During one survey of deep Arctic waters, researchers recorded a small gelatinous organism with long branching appendages that extended outward like delicate threads. The animal drifted slowly through the water column, pulsing gently as it moved. At first glance it resembled certain siphonophores known from warmer oceans, yet the branching pattern of its tentacles appeared different. The video lasted less than 30 seconds before the organism vanished into the darkness. Despite careful review by several marine biologists, the creature could not be confidently assigned to any known species. Whether it represented a rare visitor from another ocean region, or a previously undocumented Arctic resident remains unclear. Scientists sometimes describe these brief encounters as reminders of how little of the ocean has been explored. The deep Arctic basin covers millions of square kilometres. Most expeditions investigate only small areas for limited periods. A single research vehicle might explore a few kilometres of seafloor during a dive. Beyond that narrow path, countless animals continue their lives unseen. Another interesting case involved a strange translucent fish observed beneath a thick layer of sea ice. The fish appeared to possess elongated fins extending along much of its body, giving it an almost ribbon-like appearance. It moved slowly through the water near the underside of the ice, possibly feeding on small crustaceans living there. Researchers initially suspected it might belong to a group of fish adapted to cold environments with antifreeze proteins in their blood. However, the body proportions did not match known Arctic species. The encounter lasted only a few moments before the fish disappeared into the dim water. Attempts to locate similar individuals during the remainder of the expedition were unsuccessful. Such observations illustrate a pattern that occurs repeatedly in deep-sea research. The ocean reveals glimpses rather than complete stories. A camera records an unfamiliar shape drifting past. A sample retrieved from sediment contains fragments of an organism that cannot be fully identified. A hydrophone captures sounds that might belong to animals rarely seen by human observers. Each piece adds to the puzzle, but the full picture often remains incomplete. For marine scientists, this uncertainty is both challenging and fascinating. It means the Arctic Ocean still holds discoveries waiting to be confirmed. Creatures glimpsed only once may eventually appear again during future expeditions. New technologies may allow researchers to remain beneath the ice longer, or explore deeper areas previously inaccessible. Autonomous underwater vehicles capable of travelling great distances beneath the ice are already expanding the range of observation. As these tools improve, the chances of encountering rare species more than once will increase. Until then, some animals remain known only from a few seconds of footage or a single specimen collected during a brief expedition. In the quiet depths beneath Arctic ice, life continues largely unnoticed. Strange organisms drift through dark water, following patterns shaped by millions of years of evolution. Some will eventually become familiar to science, others may remain elusive for decades, and occasionally, when a research camera illuminates the darkness for a moment, an unfamiliar creature will pass through the light, offering a brief glimpse of a world that humans are only beginning to understand. In science, discovering a new animal usually follows a careful process. Researchers observe the organism, collect physical samples, compare its structure and genetic material with known species, and eventually publish a formal description that confirms its place in the biological record. Only after that process is complete does the animal become recognized as a new species. But the Arctic Ocean does not always cooperate with such orderly procedures. Sometimes scientists encounter evidence that suggests the presence of unfamiliar animals without ever obtaining the proof required for confirmation. A strange shape appears briefly on a camera. A piece of tissue appears in a net sample that does not match any known species. Unusual sounds echo through underwater microphones with no obvious source. Each of these observations hints at something unknown, yet none provides enough information to draw a final conclusion. As a result, marine researchers studying the Arctic occasionally speak about animals that might exist but have never been formally confirmed. The possibility arises partly because of how little of the Arctic Ocean has been explored in detail. Much of the seafloor lies beneath permanent or seasonal sea ice, and the depths reach several kilometres in many areas. Even modern research vessels equipped with advanced submersibles can survey only small portions of this environment during a single expedition. Between those surveyed locations stretch enormous areas that no camera has ever recorded. It would not be surprising if unfamiliar species live there. One example involves deep water squid. Squid are known to inhabit Arctic waters, but most observations come from relatively shallow regions or from animals caught accidentally in fishing equipment. The deeper parts of the Arctic basin remain difficult to sample, and several recordings from deep-sea cameras have hinted at squid-like shapes moving through the darkness far below the ice. These shapes appear only briefly, often just silhouettes illuminated by the edge of the camera's light beam. The animals seem larger than typical Arctic squid species and move with a slow, controlled propulsion through the water. Because the footage is usually brief and distant, researchers cannot clearly see details such as the arrangement of arms or the structure of the mantle. Without those details, identifying the animal becomes impossible. Some scientists suspect these sightings may represent deep-sea squid species that have never been documented in Arctic waters before. Another possibility involves large gelatinous organisms drifting through mid-water zones. The deep ocean contains many types of siphonophores, colonial animals made up of specialized individuals working together as a single organism. Some siphonophores form extremely long chains, extending dozens of meters through the water like living ribbons. In several Arctic expeditions, researchers have reported seeing faint elongated shapes on sonar or camera systems that resemble large siphonophores. However, the recordings often lack the clarity needed to confirm what the object actually was. If such animals do exist in the Arctic basin, they may be extremely delicate and difficult to capture with standard equipment. Their bodies might collapse when exposed to pressure changes during collection, leaving little evidence behind. Another category of possible but unconfirmed animals involves deep-sea fish, adapted to life in the darkest parts of the Arctic basin. Fish living at great depths sometimes display unusual features such as elongated bodies, bioluminescent organs, or extremely large sensory structures designed to detect movement in the water. Occasional camera recordings from Arctic research dives have shown fish that appear different from known species. These fish may possess unusually long fins or slender bodies that do not match the shapes typical of Arctic cod or other documented species, yet once again, the encounters are brief. The animal swims away before scientists can adjust the camera or attempt to collect a specimen. Without additional observations, researchers cannot determine whether the fish belongs to a rare species already known elsewhere, or represent something entirely new. In addition to visual sightings, acoustic monitoring has occasionally hinted at animals not yet confirmed, Hydrophones placed beneath Arctic ice capture a wide range of underwater sounds. Many recordings clearly belong to known marine mammals such as beluga whales, narwhals, or bowhead whales. But some sounds differ from those familiar patterns. Certain low-frequency pulses repeat in sequences that do not match documented whale songs. Other recordings contain short bursts of sound that resemble communication signals but cannot be linked to known species. Scientists studying these recordings usually begin by searching for environmental explanations. Ice movements, underwater landslides, or geological activity can produce unusual acoustic patterns. However, a few recordings remain difficult to categorize. One possibility is that unknown or poorly studied marine animals produce these sounds. For example, some species of fish are capable of generating rhythmic pulses by vibrating specialized muscles near their swim bladders. These pulses may serve as communication signals during mating or territorial behavior. If an Arctic fish species with such abilities has not yet been documented, its acoustic signals might appear unfamiliar in hydrophone recordings. Another intriguing possibility involves large invertebrates living near deep hydrothermal vents. Vent ecosystems in other oceans host unusual animals that rarely appear elsewhere. Giant tube worms, specialized shrimp, and other vent-dwelling organisms often display unusual shapes and behaviors. Although several hydrothermal vent fields have been discovered in the Arctic, much of the ridge system remains unexplored. It is possible that additional vent ecosystems exist beyond the areas scientists have already surveyed. If so, they may support species entirely unknown to science. Evidence for such animals might appear only indirectly at first. Water samples might contain fragments of biological material that do not match known organisms. Chemical traces in the water could suggest metabolic processes associated with unknown microbes or small animals. Until researchers locate the vent site and observe the organisms directly, these clues remain suggestive rather than conclusive. Even the underside of Arctic sea ice may hide species that scientists have not yet documented. The ice forms a complex habitat filled with narrow brine channels, where microorganisms thrive. Small crustaceans move through these channels, feeding on algae and bacteria. Because the structure of sea ice varies constantly as temperatures change, studying these habitats in detail is difficult. Scientists have collected many samples of ice-associated organisms, yet some specimens do not match previously described species. Further analysis may eventually reveal that they represent entirely new forms of life, adapted to the icy environment. In addition to biological possibilities, occasional reports from Arctic explorers and researchers mention sightings that remain ambiguous, a distant movement beneath the ice that could not be clearly identified, an unusual shadow recorded by a deep-sea camera before drifting out of view. Such observations rarely lead to sensational conclusions among scientists. Most researchers approach them cautiously, assuming that additional data will eventually reveal ordinary explanations. Still, these moments serve as reminders that the Arctic Ocean remains one of the least observed marine environments on Earth. The combination of thick ice, extreme weather, and deep water limits how frequently scientists can explore its depths. Even modern submersibles and autonomous vehicles cover only small sections of the ocean floor during each mission. Between those surveyed areas lies a vast space where life continues quietly. It is entirely possible that unfamiliar animals move through those waters today, following evolutionary paths shaped by cold temperatures and long polar winters. Some may resemble species already known from other oceans but adapted to Arctic conditions. Others may belong to lineages rarely encountered elsewhere. Eventually, as technology improves and exploration expands, many of these possibilities will likely become clearer. New expeditions will send vehicles beneath the ice for longer periods. Advanced cameras will record animals in greater detail. Genetic sampling techniques may detect traces of organisms even when they remain unseen. Each new piece of information will narrow the gap between speculation and confirmation. Until then, the Arctic Ocean remains a place where science occasionally senses the presence of something unfamiliar without yet being able to name it. Not mysterious in a dramatic sense, but simply unexplored. An environment so vast and difficult to reach that even today, beneath the frozen surface at the top of the world, there may be creatures moving through dark water that humans have never clearly observed. When most people imagine the Arctic Ocean, they picture a shallow sea covered with drifting ice. On a globe, the region appears small compared with the vast Pacific or Atlantic, and the presence of ice often gives the impression that the ocean beneath it must also be relatively simple. But the Arctic Ocean hides an unexpected depth. Beneath the ice that marks the top of the world lies a basin that plunges thousands of meters down into darkness. Much of the seafloor there has never been seen directly by human eyes. Cameras have visited small sections, research equipment has collected samples from scattered locations, yet enormous areas remain unexplored. To understand this hidden landscape, it helps to imagine the Arctic Ocean not as a flat pool of water, but as a complex terrain. Underwater mountain ranges stretch across the basin. Deep plains spread between them. In some places, the seafloor slopes gently downward, while in others it drops sharply into narrow valleys. The deepest known point in the Arctic Ocean lies within the Molloy Deep, a depression located between Greenland and the Svalbard archipelago. There, the ocean floor descends more than 5,500 meters below the surface. That is deeper than many mountains at all. Reaching such depths is extremely difficult even in open oceans. In the Arctic, the challenge becomes even greater because of the ice cover above. Research vessels must navigate through thick sea ice before they can even begin lowering instruments toward the seafloor. Once a research team arrives at a suitable location, they deploy specialized equipment capable of surviving the immense pressure found at these depths. Water pressure increases steadily with depth, and at 5,000 meters it becomes more than 500 times greater than the pressure at the ocean surface. Any device sent down must be strong enough to withstand that force. Submersible vehicles designed for deep-sea exploration often use thick metal spheres to protect sensitive electronics and cameras. Even so, operating them beneath Arctic ice requires careful planning. The vehicles must remain connected to the surface by long cables or operate autonomously before returning to a designated recovery point. Despite these difficulties, several expeditions have managed to study the deepest Arctic regions. What they have found is an environment that seems calm at first glance but contains subtle signs of life. The seafloor in these depths often appears as wide plains of fine sediment. Over thousands of years, tiny particles drifting down through the ocean have settled there, creating layers of soft mud. These particles include fragments of dead plankton, pieces of algae, and organic material carried by currents from distant parts of the ocean. This slow rain of material forms the primary food supply for animals living on the deep Arctic seabed. Because the supply arrives gradually, many deep-sea creatures live slow, energy-efficient lives. Sea cucumbers are among the most common inhabitants. These animals crawl slowly across the sediment, collecting organic particles with feeding tentacles surrounding their mouths. Their bodies resemble soft cylinders that stretch and contract as they move. At great depths in the Arctic basin, certain sea cucumber species gather in loose groups that resemble small herds moving across the ocean floor. Researchers observing them through deep-sea cameras sometimes describe the scene as surprisingly peaceful. The animals move so slowly that minutes may pass before any visible change occurs. Brittle stars also inhabit these depths. Unlike sea cucumbers, brittle stars possess long, flexible arms extending outward from a small central body. They spread these arms across the sediment to capture drifting particles of food. When a particle touches one of the arms, the brittle star quickly transfers it toward its mouth. In some deep Arctic regions, brittle stars appear in large numbers, covering sections of the seabed like delicate star-shaped mosaics. Another group of animals common in these depths includes polychaete worms. Many polychaetes construct tubes made from sediment particles. From inside these tubes they extend feathery appendages that collect food from the surrounding water. Others roam freely across the seabed, searching for organic material or smaller prey. Despite their modest appearance, these worms play an important role in recycling nutrients within the deep-sea ecosystem. By feeding on organic debris and breaking it down further, they help maintain the balance of the environment. Crustaceans also inhabit the deep Arctic basin. Amphipods and isopods move across the sediment searching for food. Their bodies are adapted to withstand extreme pressure, and many species grow larger in cold environments. Some amphipods become especially active when larger animals die and sink toward the seafloor. A single whale carcass reaching the deep Arctic floor can attract dozens or even hundreds of scavengers within a short period. These events provide rare bursts of abundant food in an otherwise resource-limited environment. Fish living in the deepest Arctic waters remain relatively rare compared with shallower regions, but several species have been recorded. These fish often possess elongated bodies and reduced skeletal structures suited to high-pressure conditions. Some species also produce antifreeze proteins that prevent ice crystals from forming in their tissues when they move into slightly colder water layers. Because food is scarce in deep environments, many deep-sea fish adopt a patient hunting strategy. Instead of chasing prey over long distances, they remain still and wait for smaller animals to drift close enough to capture. The darkness in these depths is complete. Sunlight disappears within the first few hundred meters of water. Beyond that point, the ocean becomes a permanent night where animals rely on senses other than vision. Some species detect vibrations in the water, others sense chemical traces released by prey or potential mates. Bioluminescence also appears among certain deep Arctic organisms. Small flashes of blue or green light may briefly illuminate the water as creatures communicate or defend themselves against predators. But even these faint glows are rare in the deepest parts of the basin, where many animals conserve energy by remaining still and producing no light at all. Another feature of the deep Arctic environment involves slow geological processes. The seafloor in this region continues to shift as tectonic plates move beneath the ocean. Along underwater ridges such as the Gackle Ridge, new crust forms gradually as molten material rises from below. Hydrothermal vents occasionally appear along these ridges, releasing mineral-rich water into the surrounding ocean. Although vent ecosystems provide localized bursts of activity, most of the deep Arctic floor remains relatively quiet. Sediment accumulates slowly. Animals move gradually across the seabed. Currents drift through the water above, carrying microscopic particles that eventually settle downward. Time seems to pass differently in these depths. Some deep-sea animals grow extremely slowly and may live for decades or even centuries. Greenland sharks, which occasionally descend into deep Arctic waters, represent one of the most remarkable examples. Studies suggest that certain individuals may live several hundred years, making them among the longest-lived vertebrates known. While sharks usually swim above the deepest plains, their presence reminds researchers that even large predators sometimes visit these remote environments. Another curious aspect of the deep Arctic basin involves its isolation. Because the Arctic Ocean connects to other oceans through relatively narrow passages, water exchange occurs slowly compared with open ocean systems. This isolation may allow certain species to evolve independently over long periods. Some organisms discovered in deep Arctic waters appear closely related to species found elsewhere, while others display subtle differences suggesting long-term separation. Understanding these evolutionary relationships requires detailed genetic studies. Researchers collect small samples during expeditions and analyze the DNA of various organisms to determine how they are related. Sometimes the results reveal surprising connections between Arctic species and animals living in distant oceans. Other times, the genetic data suggests that certain species may have evolved uniquely within the Arctic basin itself. Despite all these discoveries, large portions of the deep Arctic Ocean remain unexplored. Mapping missions have identified underwater ridges and valleys that have never been visited by submersible vehicles. Sediment cores collected from certain regions hint at ecosystems that may differ from those already studied. Future expeditions will likely reveal additional species living quietly across the deep sea floor. The combination of depth, ice cover, and extreme conditions ensures that exploration will continue slowly. Yet each mission adds new pieces to the growing understanding of the Arctic Ocean. The frozen surface above may appear simple and silent, but thousands of meters below it lies a world shaped by darkness, pressure, and patience. Animals move through that world in ways that rarely intersect with human activity. And somewhere within those deep basins, beneath drifting ice and cold currents, life continues following rhythms that have remained unchanged for ages, far longer than human exploration itself. For most of modern history, the Arctic Ocean remained protected by something simple but powerful: ice. Thick layers of sea ice covered much of the region year-round, forming a natural barrier that limited both human activity and scientific observation. Ships struggled to reach the central basin, and even when they did, exploring beneath the frozen surface remained extremely difficult. The ice made the Arctic remote, unpredictable, and largely untouched. Over the last few decades, however, scientists have begun observing a noticeable shift in that frozen landscape. Temperatures in the Arctic are rising faster than in many other parts of the world, and one of the most visible consequences has been the gradual reduction of sea ice. Each summer the ice retreats farther than it once did. Areas that were once sealed beneath thick ice now experience longer periods of open water. The seasonal ice also forms later in the year and melts earlier in the spring. For wildlife living in the Arctic, these changes create both challenges and opportunities. For scientists studying the ocean beneath the ice, the changes are revealing parts of the ecosystem that had remained hidden for centuries. One of the first ways climate change has exposed new Arctic species involves simple accessibility. As sea ice thins or retreats, research vessels gain access to regions that were previously unreachable. Icebreakers can now travel deeper into the Arctic basin during summer months, allowing scientists to deploy equipment in places where no instruments had been placed before. Every time researchers reach one of these newly accessible areas, they encounter organisms that have rarely or never been studied. Some of these animals are not new to the Arctic at all. They have simply lived in areas that humans could not easily reach. For example, deep-sea sampling in previously ice-covered regions has uncovered unfamiliar crustaceans, worms, and small fish species inhabiting the sea floor. These discoveries often occur when sediment cores or collection nets bring up animals that scientists cannot immediately identify. Once the specimens are examined in laboratories, researchers sometimes realize they represent species not yet described in scientific literature. Other discoveries come from underwater cameras exploring beneath floating ice remnants. Remotely operated vehicles lowered into these environments occasionally record gelatinous organisms drifting through the water column or unfamiliar fish moving close to the seabed. Because such regions were historically difficult to explore, many of the animals recorded in these missions appear for the first time in scientific records. Another way climate change reveals hidden species involves the movement of animals into new areas. As Arctic waters warm slightly and sea ice retreats, some marine species from more southern oceans begin expanding their range northward. Fish species that once remained in subarctic waters are now occasionally found deeper within the Arctic basin. For example, Atlantic cod and certain types of plankton have been observed moving into areas where they were previously rare. When these newcomers arrive, they sometimes encounter ecosystems that developed in relative isolation. Scientists studying these interactions often discover previously overlooked species living within those ecosystems. In some cases, the arrival of new animals draws attention to food chains that had not been fully understood before. For instance, when larger fish appear in a region, researchers may study the smaller animals those fish feed on. During such investigations, previously unknown species of crustaceans or plankton may be identified. Climate change has also altered the structure of sea ice itself, which influences the microscopic communities living within it. Sea ice contains narrow channels filled with salty brine where bacteria, algae, and small organisms thrive. These communities form the base of under-ice ecosystems. As temperatures rise and ice becomes thinner or more fragmented, the conditions inside those brine channels change. Researchers studying melting ice have discovered unusual microbial species that were previously hidden within the frozen structure. Some of these microorganisms possess biochemical adaptations, allowing them to survive in extremely salty and cold conditions. Their existence offers insight into how life adapts to environments that fluctuate between freezing and thawing. In addition, the melting of multi-year ice has revealed habitats that were once permanently sealed. Multi-year ice refers to ice that survives several summers without melting completely. This type of ice can grow several meters thick and may remain in place for many years. When multi-year ice melts, the ocean beneath becomes exposed for the first time in decades. Scientists exploring such newly opened areas sometimes find biological communities that developed beneath the ice over long periods. These communities include unusual combinations of plankton, crustaceans, and microbial life adapted to the stable conditions beneath thick ice. Once the ice disappears, those ecosystems may change rapidly. Another important factor involves sunlight. Thinner ice allows more sunlight to penetrate into the ocean below. This increase in light can stimulate phytoplankton blooms in areas where photosynthesis was previously limited. When phytoplankton populations grow, they support larger populations of zooplankton and other small animals. As scientists study these blooms, they often identify microscopic species that were previously unknown in the region. Some of these organisms may have existed there all along but remained undetected because earlier research focused on different locations. Climate change has also revealed previously hidden seafloor features. In some regions where glaciers once extended into the ocean, retreating ice has uncovered underwater ridges and valleys. These newly exposed habitats may host communities of animals that lived in isolation beneath thick glacial ice. When research teams explore these areas, they sometimes encounter unusual species adapted to extremely cold and stable conditions. The discovery of such organisms adds new layers to the understanding of Arctic biodiversity. However, the appearance of hidden species does not necessarily mean that climate change benefits Arctic ecosystems. In many cases, environmental shifts place stress on animals that evolved to survive under stable ice conditions. Species dependent on sea ice for shelter or hunting platforms may struggle as ice disappears. At the same time, newly arriving species from warmer oceans may compete with native Arctic animals for food and habitat. Scientists studying these changes emphasize that discovering new species does not mean the environment is improving. Rather, it reflects how little of the Arctic has been explored and how quickly conditions there are changing. In some cases, the animals being discovered today may have existed quietly beneath the ice for thousands of years. The melting of ice simply allows humans to see them for the first time. One interesting example involves under-ice phytoplankton blooms discovered in the last decade. For many years, scientists believed that thick Arctic ice prevented significant phytoplankton growth until the ice melted. But recent observations reveal that large blooms can occur beneath thin ice layers, where sunlight passes through small openings in the snow and ice above. These blooms support communities of zooplankton and fish that had previously gone unnoticed. The discovery changed how researchers understand energy flow within the Arctic ecosystem. It also demonstrated that important biological processes may occur in places scientists had rarely observed before. Another example involves deep-sea sponges discovered on previously unexplored seafloor ridges. Some Arctic sponge species grow slowly and may live for centuries. They create habitats for smaller animals such as crustaceans and worms. When new seafloor areas became accessible due to changing ice conditions, researchers found sponge communities that had never been documented. Each new discovery adds to the picture of the Arctic as a complex and dynamic environment, rather than a simple frozen ocean. Still, scientists remain cautious about interpreting these findings. The Arctic ecosystem evolved under conditions of long winters, thick ice cover, and relatively stable temperatures. Rapid changes may disrupt those patterns in ways that are not yet fully understood. Some species may expand their range as new habitats appear, others may struggle to adapt. What remains clear is that climate change is opening windows into parts of the Arctic Ocean that humans rarely saw before. Research ships now travel routes that were blocked by ice only a few decades ago. Submersibles explore underwater landscapes once sealed beneath glaciers. Cameras capture images of animals living in regions that had remained hidden for centuries. Each observation reveals more about the life that has always existed beneath the frozen roof of the Arctic. And as these windows continue to open, scientists are developing new technologies designed to explore even deeper beneath the ice, searching for organisms and ecosystems that remain beyond the reach of current expeditions. Exploring the Arctic Ocean has always required patience and creativity. For centuries, reaching the region itself was the greatest challenge. Ships struggled to move through ice, and even when explorers managed to arrive, they could only observe what existed at the surface. The ocean beneath the ice remained hidden. Today, scientists still face many of the same obstacles. Thick sea ice, freezing temperatures, and long periods of darkness make the Arctic one of the most difficult environments on Earth to study. Yet over the past several decades, researchers have developed an impressive collection of technologies designed specifically to explore this frozen ocean. Each tool opens a small window into the world beneath the ice. One of the most important pieces of equipment used in Arctic research is the icebreaker. An icebreaker is a specialized ship designed to travel through thick sea ice. Unlike ordinary vessels, icebreakers have reinforced hulls and powerful engines that allow them to push through frozen surfaces. The shape of the ship's bow is carefully engineered. Instead of cutting through the ice like a knife, the ship rides up onto the ice and uses its weight to break the frozen sheet beneath it. As the ice fractures, the vessel slowly moves forward. This method allows research teams to reach parts of the Arctic Ocean that would otherwise remain inaccessible. Many scientific expeditions rely on icebreakers to transport researchers, equipment, and submersible vehicles into the central Arctic basin. Once the ship reaches a suitable location, scientists begin deploying other tools. One of the most commonly used devices in ocean research is the CTD instrument. The name CTD refers to the three measurements it collects: conductivity, temperature, and depth. Conductivity reveals the salt content of seawater. Temperature indicates how warm or cold the water is at different depths. Depth measurements help researchers build detailed profiles of the water column. The CTD instrument is usually lowered from the side of a ship using a strong cable. As it descends through the water, sensors record environmental conditions at every level. Attached to the CTD frame are bottles that capture water samples from specific depths. These samples allow scientists to analyze nutrients, microscopic organisms, and chemical compounds present in the ocean. Although the CTD does not capture animals directly, it provides essential information about the environment where those animals live. Understanding water conditions helps researchers predict where certain species might be found. To observe the animals themselves, scientists often rely on remotely operated vehicles, commonly known as ROVs. An ROV is essentially a robotic submarine connected to the surface by a cable. The cable carries power and allows operators on the ship to control the vehicle. ROVs are equipped with cameras, lights, and mechanical arms. The cameras provide live video feeds from the ocean depths, allowing scientists to see creatures moving through the water or crawling along the seafloor. The mechanical arms can collect samples of sediment, rocks, or biological specimens. Bright lights mounted on the vehicle illuminate the darkness beneath the ice. For many researchers, watching the live camera feed from an ROV dive is one of the most exciting moments of an expedition. The screen may suddenly reveal a strange jellyfish drifting through the water or a cluster of unfamiliar animals gathered around a rock formation. Because ROVs remain connected to the surface, their range is limited by the length of their cable. To explore larger areas, scientists sometimes use autonomous underwater vehicles, or AUVs. Unlike ROVs, AUVs operate independently after being launched from a ship. They follow pre-programmed routes beneath the ice, collecting data with cameras, sonar systems, and environmental sensors. Once the mission is complete, the vehicle returns to a predetermined location where researchers retrieve it. AUVs allow scientists to map large sections of the seafloor or explore areas beneath thick ice where cables might become entangled. Some AUVs are designed to travel for many hours before returning to the surface. Another important technology used in Arctic exploration is sonar. Sonar stands for sound navigation and ranging. Because light does not travel far in deep ocean water, sonar uses sound waves to detect objects and map underwater landscapes. A sonar device sends out pulses of sound. When those pulses strike the sea floor or an object in the water, they bounce back toward the instrument. By measuring how long it takes for the echo to return, scientists can calculate the distance to the object. This technique allows researchers to create detailed maps of underwater terrain. In the Arctic, sonar has been used to reveal mountain ranges, valleys, and hydrothermal vent fields hidden beneath the ice. Some sonar systems can even detect large animals swimming through the water column. For studying marine mammals and other sound-producing animals, scientists rely on hydrophones. Hydrophones are underwater microphones designed to capture sound travelling through water. They can record whale calls, fish communication signals, and the grinding noises produced when sea ice shifts under pressure. Hydrophones may be deployed from ships, attached to drifting buoys, or anchored to the seafloor for long-term monitoring. By analysing these recordings, researchers can learn about animal behaviour and migration patterns even when direct visual observation is impossible. Another fascinating tool used in Arctic research involves satellite technology. Satellites orbiting the Earth continuously observe the polar regions from space. They provide information about sea ice coverage, ocean temperature, and the movement of ice flows across the Arctic basin. High-resolution satellite images allow scientists to identify open water areas known as leads, where ice has cracked apart. These leads often serve as entry points for research equipment or as feeding grounds for marine animals. Satellites also track large animals fitted with small electronic tags. Researchers attach these tags to whales, seals, or other marine creatures to monitor their movements. Each tag transmits location data to satellites, allowing scientists to follow the animals' journeys across the Arctic Ocean. These tracking studies reveal migration routes, feeding areas, and how animals respond to changes in sea ice. In addition to observing animals directly, scientists sometimes study traces of life left behind in the water. Environmental DNA analysis, often called eDNA, has become an increasingly valuable technique. Every organism sheds tiny fragments of genetic material into the environment through skin cells, waste, or mucus. By collecting water samples and analysing the DNA fragments within them, researchers can detect the presence of species that may not have been seen directly. For example, if a rare fish species passes through an area, it may leave behind microscopic traces of DNA in the water. Even if the fish itself is never captured on camera, scientists can confirm its presence through genetic analysis. This method is especially useful in the Arctic, where direct observation opportunities are limited. Researchers have also developed specialised underwater observatories that remain in place for long periods. These observatories consist of cameras, sensors, and communication equipment anchored to the seafloor or attached to ice platforms. They record environmental conditions and biological activity continuously. Because the Arctic environment changes throughout the year, long-term monitoring is essential for understanding seasonal patterns. An observatory may record months of quiet winter darkness, followed by sudden bursts of biological activity when sunlight returns. One of the most ambitious technological efforts in Arctic exploration involves ice-tethered platforms. These platforms drift with sea ice while collecting data from the surrounding ocean. Sensors suspended beneath the ice measure water temperature, salinity, and nutrient levels. Some platforms also include cameras or acoustic instruments. As the ice moves across the Arctic basin, the platform travels with it, collecting information from different regions. Eventually, the equipment is recovered and the recorded data analysed. All of these technologies work together to expand scientific understanding of the Arctic Ocean. An expedition might begin with satellite images identifying an area of interest. An icebreaker carries researchers into the region. Sonar maps the seafloor while AUVs explore beneath the ice. Rovers capture video of unfamiliar creatures. Hydrophones record the sounds of whales passing through dark water. Water samples reveal microscopic organisms through DNA analysis. Each tool contributes another piece of information. Gradually, scientists assemble these pieces into a clearer picture of life beneath the Arctic ice. Yet even with all these advances, exploration remains incomplete. Large portions of the Arctic Ocean have never been visited by submersible vehicles. Many deep basins remain mapped only in rough detail. Animals captured briefly on camera may never be seen again. The technology allows humans to observe the Arctic in ways earlier explorers could never imagine. Still, the frozen ocean continues to hold many secrets, and with every new expedition, researchers hope that the next descent into the dark water beneath the ice will reveal something no one has ever seen before. The idea that prehistoric creatures might still survive in remote corners of the Earth has fascinated people for generations. Stories about hidden dinosaurs in unexplored jungles or giant sea monsters in deep oceans often appear in books and films. Most of these ideas belong more to imagination than science, yet the question itself is not entirely unreasonable. The Earth's oceans are vast and large portions of them remain unexplored. The Arctic Ocean in particular presents conditions that could allow certain ancient lineages to persist quietly for long periods. Thick sea ice, extreme cold, and limited human activity have kept the region relatively isolated compared with other marine environments. Because of this isolation, some species living there today resemble organisms that existed millions of years ago. This does not mean dinosaurs or mythical monsters are swimming beneath the ice. Evolution rarely leaves species unchanged for such enormous spans of time. However, certain animals, known as living fossils, display body structures very similar to those of their distant ancestors. Studying these creatures offers a glimpse into evolutionary history. One example involves the Greenland shark. This slow-moving predator inhabits deep Arctic and North Atlantic waters. It may not appear particularly ancient at first glance, but its life history is remarkable. Scientists studying the shark's eye tissues have estimated that some individuals live for several centuries. If these estimates are correct, certain Greenland sharks swimming today may have been born during the early modern period of human history. The species itself belongs to a lineage of sharks that has existed for tens of millions of years. Although the animals have evolved over time, their overall body design remains similar to that of ancient relatives found in fossil records. Another example of ancient lineage survival involves certain deep-sea sponges discovered in Arctic waters. Sponges are among the oldest forms of multicellular life on Earth. Fossil evidence suggests that sponge-like organisms existed more than 600 million years ago, long before the appearance of complex animals such as fish or reptiles. Some Arctic sponge species grow extremely slowly and may live for centuries. Their simple body structure has remained relatively unchanged through vast stretches of evolutionary time. These animals filter water continuously, extracting tiny particles of food. Their persistence in deep Arctic environments demonstrates how ancient biological strategies can remain effective in stable conditions. The deep ocean itself provides a kind of refuge for certain evolutionary lineages. Unlike surface environments where temperatures fluctuate and ecosystems change rapidly, deep-sea habitats often remain relatively stable for long periods. Temperature variations are minimal, sunlight never reaches the seafloor, and many geological features change slowly. Such stability can allow ancient groups of organisms to survive with fewer dramatic adaptations. For instance, certain types of marine worms living near hydrothermal vents in the Arctic resemble relatives found in ancient fossil deposits. While these worms are not identical to their prehistoric ancestors, their general body structure remains surprisingly consistent. Similarly, some species of crustaceans inhabiting deep Arctic waters belong to groups that have existed since the age of the dinosaurs. These animals have evolved gradually over time, but their overall anatomy retains features that paleontologists recognize from fossil specimens. The persistence of such lineages sometimes leads to speculation about whether even older creatures might survive in unexplored environments. After all, scientists continue discovering new species in deep oceans around the world. Each expedition reveals organisms that were previously unknown simply because no one had searched those particular habitats before. The Arctic Ocean contains vast areas that remain poorly studied. Its deep basins, underwater ridges, and isolated vent systems could theoretically support species that scientists have not yet documented. However, the likelihood of truly prehistoric animals surviving unchanged for millions of years is extremely small. Evolution tends to modify species gradually as environments shift. Even in stable habitats, genetic changes accumulate over time. The animals living in the Arctic today may resemble ancient forms, but they are modern species that have adapted to current conditions. Still, the concept of ancient lineages surviving in remote environments has real scientific examples. One famous case involves the coelacanth. For decades, this fish was believed to have gone extinct with the dinosaurs about 66 million years ago. Fossil records suggested that coelacanths had disappeared entirely. Then, in 1938, a living specimen was discovered near the coast of South Africa. The discovery astonished scientists. Coelacanths were not truly prehistoric survivors frozen in time, but they belonged to a lineage that had persisted far longer than previously known. Although coelacanths inhabit warmer waters rather than the Arctic, their story illustrates how incomplete scientific knowledge can be. The deep ocean still holds many surprises. In Arctic environments, similar discoveries are possible, though perhaps less dramatic. Researchers exploring deep basins sometimes encounter fish or invertebrates that appear unfamiliar at first glance. Genetic studies later reveal that these animals belong to branches of evolutionary trees with ancient origins. For example, certain Arctic mollusks and echinoderms trace their ancestry back hundreds of millions of years. Their modern representatives continue living quietly on the seafloor. Another intriguing possibility involves microorganisms. Bacteria and other microscopic life forms can survive in extreme environments for long periods. Some species living in Arctic sediments or ice layers may have existed in similar forms for millions of years. These microbes evolve slowly compared with more complex organisms. Studying them can provide clues about ancient ecosystems. In addition, Arctic hydrothermal vents create conditions similar to environments that may have existed early in Earth's history. Some scientists believe life itself may have originated near hydrothermal systems billions of years ago. The microbes and animals living around Arctic vents today may represent distant relatives of those early life forms. By studying them, researchers gain insight into how life adapts to extreme environments. There are also curious cases of animals rediscovered after long periods without observation. Marine species sometimes disappear from scientific records for decades before being encountered again. These Lazarus species, named after the biblical figure brought back to life, remind scientists that the ocean can hide organisms for surprisingly long periods. The Arctic Ocean's isolation increases the chances of such rediscoveries. Limited human presence means that species living in remote basins may rarely interact with research equipment. Only when scientists explore those specific regions do they become aware of the animals inhabiting them. Another factor supporting the persistence of ancient lineages in the Arctic involves temperature. Cold environments slow many biological processes. Metabolism operates at a slower rate, growth occurs gradually, and organisms may live longer than their relatives in warmer climates. These conditions can create populations that change slowly over evolutionary time. The result is species that appear ancient in form, even though they continue evolving. Researchers sometimes describe this pattern as evolutionary conservatism. Certain body structures remain effective in particular environments, so natural selection does not drastically alter them. Animals with such traits may resemble their distant ancestors more closely than species living in rapidly changing ecosystems. Even so, it is important to distinguish between ancient lineages and prehistoric survivors. Ancient lineages are groups of organisms that have existed for millions of years but continue evolving along the way. Prehistoric survivors, in the sense of animals unchanged since ancient times, rarely exist. Nature constantly adjusts species to new conditions. The Arctic Ocean illustrates this principle well. Many creatures living beneath the ice carry genetic histories stretching far back in time. Their ancestors may have lived during periods when Earth climate was very different from today, but the animals themselves are products of ongoing evolution. They have adapted to cold temperatures, limited food supplies, and long polar winters. Their existence demonstrates resilience rather than stagnation. In that sense, the Arctic does not preserve prehistoric life exactly as it once existed. Instead, it shelters lineages that have persisted through countless environmental changes. Studying those lineages helps scientists understand how life adapts to extreme conditions and how ecosystems evolve over long periods. And while the chances of encountering a true prehistoric creature remain extremely small, the Arctic Ocean still holds many mysteries. Deep basins remain unexplored, hydrothermal vents continue to be discovered, and unfamiliar organisms occasionally appear on research cameras. Each expedition brings the possibility of encountering species whose evolutionary history stretches far into the past. Not relics frozen in time, but living reminders that the story of life on Earth extends much further back than human exploration of the polar seas. Long before scientists placed cameras beneath the ice, or satellites began mapping the polar seas from space, the Arctic already existed in stories. Travellers returning from northern voyages spoke about strange lights in the sky, unfamiliar animals in the water, and sounds echoing across frozen landscapes. These accounts spread through villages, ports, and early maps, gradually turning into legends. Some of these stories sounded exaggerated or mysterious. Yet when scientists examine them today, many of the details appear less mysterious and more like early attempts to describe natural phenomena that people did not yet understand. The Arctic has always been a place where observation and imagination easily blend together. Part of the reason lies in how unfamiliar the environment can feel to newcomers. The landscape contains long periods of darkness, shifting ice, and enormous distances without landmarks. Sounds travel strangely across frozen surfaces. Lights dance across the sky in unpredictable patterns. Animals appear briefly before disappearing into the water or snow. In such conditions, stories naturally develop. One of the most famous examples involves sea serpents. For centuries, sailors crossing northern oceans reported seeing long shapes moving through the water. Some described enormous creatures rising briefly above the waves before diving again beneath the surface. These reports appeared frequently in old maritime logs and early natural history books. At the time, many people believed such creatures were real sea monsters. Modern science offers simpler explanations. Large marine animals such as whales, especially when seen from a distance in rough seas, can appear very different from their actual shape. A whale surfacing in several sections, first the head, then the back, then the tail, might resemble a long serpentine body moving through the water. In addition, certain species of giant squid possess long arms that trail behind them when swimming near the surface. Under poor visibility conditions, these animals might easily be mistaken for something entirely unfamiliar. Still, the persistence of sea serpent stories suggests that sailors were observing real animals, even if their descriptions became exaggerated over time. Another Arctic legend centers around mysterious lights moving across the sky. Indigenous communities across the Arctic have long told stories about the aurora borealis, the colourful light displays that appear in polar skies. different cultures interpreted these lights in different ways. Some traditions describe them as spirits dancing above the world. Others imagine them as signals from ancestors or reflections of distant fires. These stories were not attempts to explain the aurora scientifically. Instead, they represented ways of understanding a phenomenon that was both beautiful and unpredictable. Today, scientists know that the aurora forms when charged particles from the sun interact with Earth's magnetic field and atmosphere. Yet the ancient stories still capture something important. Anyone who has watched the aurora move silently across a winter sky understands why early observers connected the lights with powerful forces beyond ordinary experience. There are also stories about unusual sounds travelling through the ice. Explorers crossing frozen seas often reported hearing distant booms, creaks, and humming vibrations coming from beneath their feet. Some described the ice as if it were alive, producing strange noises that seemed to move across the landscape. Before scientists understood the mechanics of sea ice, these sounds could easily inspire imaginative explanations. In reality, the ice itself generates many of these noises. When temperatures change, the ice expands and contracts. Large sheets press against one another as wind and currents shift their positions. Cracks open suddenly across the surface, releasing energy that travels through the frozen sheet. These processes produce sounds that may echo across great distances. Hydrophones placed beneath the ice today record similar noises as vibrations travelling through water and ice layers. What once seemed mysterious now appears as a natural consequence of a constantly moving frozen ocean. Another category of Arctic stories involves unusual animals. Indigenous communities often describe creatures that live beneath the ice or far out at sea. Some of these stories may refer to animals now familiar to science but rarely seen by early observers. Narwhals provide a good example. These whales possess long, spiral tusks extending from their heads. When early sailors encountered narwhal tusks, they sometimes believed they had discovered the horns of mythical unicorns. In fact, narwhal tusks were traded across Europe during the Middle Ages as supposed unicorn horns. The animal itself remained little known to people outside Arctic regions. Similarly, large whales occasionally appeared in early stories as enormous sea creatures capable of overturning boats or creating powerful waves. Bowhead whales and other Arctic species can reach impressive sizes, and their behaviour near the surface might easily inspire dramatic descriptions. Yet the purpose of such stories was not necessarily to frighten or exaggerate. Many Arctic traditions served as ways to share practical knowledge about the environment. For instance, some stories warned travellers about areas where ice might break unexpectedly, or where dangerous currents existed beneath the frozen surface. By embedding these warnings in memorable narratives, communities passed important survival information from one generation to the next. In this sense, myths functioned as tools for teaching. A story about a dangerous spirit beneath the ice might encourage children to avoid thin ice zones where seals created breathing holes. A tale describing powerful animals near certain waters might remind hunters to approach those areas cautiously. Even the legends about mysterious sounds could carry practical lessons. Listening carefully to the ice helped travellers detect shifting pressure ridges or cracks forming beneath their feet. Modern researchers studying Arctic cultures often emphasise that traditional knowledge should not be dismissed simply because it appears in the form of stories. Many indigenous communities possess detailed understanding of sea ice behaviour, animal migration patterns and weather changes. These observations developed over centuries of living in close contact with the environment. Sometimes scientific research later confirms patterns that local traditions had described long before. For example, hunters have long known that certain whales travel beneath ice in predictable seasonal routes. Modern satellite tracking of marine mammals has confirmed many of these migration pathways. Similarly, traditional knowledge about the formation of sea ice and the movement of currents has proven valuable for researchers studying Arctic climate systems. In this way, stories and science can complement each other. Stories capture human experience and observation in memorable forms. Science examines those observations through systematic investigation. Both approaches contribute to understanding the Arctic. There are also myths about entire lands hidden within the polar seas. Historical maps sometimes depicted imaginary islands or open oceans near the North Pole. Explorers searching for these places occasionally encountered strange atmospheric effects such as mirages. In polar environments, layers of cold and warm air can bend light in unusual ways. Distant objects may appear stretched, floating above the horizon, or duplicated. These optical illusions, known as fata morgana mirages, could easily convince travellers that land existed where none was present. When ships sailed toward the apparent land, it would vanish as the atmospheric conditions changed. Such experiences added to the sense that the Arctic contained hidden places. In truth, the environment itself created visual tricks that misled observers. Even today, Arctic explorers occasionally witness these mirages, seeing distant ice ridges or mountains distorted into unfamiliar shapes. Perhaps the most interesting aspect of Arctic myths is how often they reflect real encounters with nature. The sea serpent may have been a whale or squid glimpsed under difficult conditions. The mysterious humming beneath the ice may have been the sound of shifting ice plates or distant whale calls. The glowing spirits in the sky were the aurora borealis dancing through the atmosphere. Each story represents a moment when someone tried to interpret something unfamiliar. Without modern instruments or scientific frameworks, people relied on imagination, memory, and shared experience. Over time, these interpretations became part of cultural tradition. Today, scientific exploration continues uncovering the realities behind many of these old observations. Cameras reveal animals that once appeared only briefly at the surface. Hydrophones capture underwater sounds once described as mysterious echoes. Satellites map the movements of sea ice that once seemed unpredictable. Yet the Arctic still retains a sense of mystery. Large areas of the ocean remain unexplored. Strange animals occasionally appear on research cameras. Unfamiliar sounds echo through underwater recordings. In that sense, the stories told by early observers were not entirely wrong. They were simply early attempts to describe a place that humans had not yet fully understood. And as researchers continue exploring beneath the ice, some of those ancient questions about what lives in the far north remain open, waiting for new discoveries to bring clearer answers. For centuries, the Arctic Ocean appeared to be one of the quietest places on Earth. Thick ice sealed the surface, storms swept across empty horizons, and only a small number of explorers ever reached the central regions of the Polar Sea. From that distant perspective, the frozen ocean looked almost unchanged from year to year. Yet the more scientists study the Arctic, the clearer it becomes that the region is still full of unanswered questions. Many of the discoveries made so far have come from brief expeditions, short camera dives, or limited sampling missions. A research ship may spend several weeks in one area, gather data, and then leave before winter ice closes the route again. Even during successful expeditions, scientists are only observing tiny portions of a vast ocean. Between those scattered observations lie enormous regions that remain largely unexplored. Because of that, researchers expect that many future discoveries still wait beneath the Arctic ice. One of the most likely areas for new discoveries involves deep-sea biodiversity. Each time scientists explore a previously unvisited section of the seafloor, they often find species that had never been recorded before. Sometimes the animals belong to familiar groups such as worms, crustaceans, or mollusks, but their exact form differs enough to represent a new species. Other times, the discoveries involve organisms that appear unusual even compared with known relatives. Deep Arctic basins, underwater ridges, and hydrothermal vent systems may all host communities that scientists have barely begun to study. The reason for this is simple. The deep ocean covers an enormous area, and research vehicles can only explore small portions of it during each mission. A single dive by a remotely operated vehicle might examine a few hundred meters of sea floor. Beyond that narrow path, thousands of square kilometers remain unseen. As exploration continues, Those unseen areas may reveal new forms of life adapted to extreme pressure, cold temperatures, and darkness. Another field where discoveries are expected involves microscopic organisms. In recent years, scientists have realized that microbial life in the Arctic is far more complex than previously believed. New genetic techniques allow researchers to analyze DNA fragments found in water samples, revealing the presence of microorganisms that cannot easily be observed under a microscope. These studies have already uncovered thousands of microbial species living beneath the ice. Many of them perform essential roles in nutrient cycling and energy transfer within the Arctic ecosystem. Future research may reveal entirely new biochemical processes used by these microbes to survive in freezing environments. Such discoveries could have implications far beyond the Arctic itself, influencing fields such as medicine, biotechnology, and environmental science. Another promising area of exploration involves hydrothermal vent systems. Only a small number of Arctic vent fields have been discovered so far, primarily along underwater ridges such as the Gackle Ridge. These vents release mineral-rich water from deep within the Earth's crust, creating unique ecosystems based on chemical energy rather than sunlight. In other oceans, hydrothermal vents host animals that exist nowhere else on Earth. Giant tube worms, specialized shrimp, and unusual microbial communities thrive in those environments. Because large sections of the Arctic ridge system remain unexplored, scientists believe additional vent ecosystems may still be waiting to be discovered. Each new vent field could reveal species that evolved in isolation beneath the ice. Researchers are also interested in exploring the underside of sea ice itself. For many years, scientists assumed that thick Arctic ice blocked most biological activity in the ocean below. Recent studies have shown that this assumption was incomplete. Microscopic algae grow within brine channels inside the ice. Small crustaceans graze on these algae, forming the foundation of under-ice food chains. In some cases, large phytoplankton blooms occur beneath thinning ice layers, where sunlight can penetrate through cracks and melt ponds. These discoveries suggest that under-ice ecosystems may be more active than previously thought. Future missions using autonomous vehicles capable of travelling long distances beneath the ice could reveal entire communities living along the frozen underside. Another area of potential discovery involves animal behaviour. Many Arctic species move beneath the ice in ways that are difficult to observe directly. Whales travel long distances through underwater corridors. Fish gather beneath ice ridges where food becomes concentrated. Seals maintain breathing holes and hidden routes through the frozen surface. With improved tracking technology, scientists can attach small sensors to animals and monitor their movements across the Arctic basin. Satellite tags already allow researchers to follow whales and seals as they travel thousands of kilometers through polar waters. As these technologies improve, scientists may uncover migration routes and feeding grounds that were previously unknown. Understanding these patterns is important not only for biological knowledge but also for conservation. The Arctic environment is changing rapidly, and many species depend on specific habitats within the ice-covered ocean. Future discoveries may also come from entirely new technologies. Autonomous underwater vehicles are becoming more advanced each year. Some designs are capable of travelling for long periods beneath ice without direct human control. Others use artificial intelligence to identify interesting objects or organisms while exploring. These vehicles could one day map large sections of the Arctic seafloor automatically, recording video and environmental data along the way. Another promising technology involves permanent underwater observatories. Scientists have begun installing monitoring stations on the Arctic seafloor equipped with cameras, sensors, and acoustic instruments. These stations record environmental changes continuously, even during the long winter darkness when research ships cannot reach the area. Over time, the data collected by these observatories will provide detailed information about seasonal cycles, animal activity, and ocean conditions. One of the most exciting possibilities for future research involves discovering species that have never been observed before. Because the Arctic Ocean remained isolated for long periods, Some ecosystems may contain organisms that evolved independently from those in other oceans. Even small discoveries can change scientific understanding. Finding a new species of crustacean might reveal unexpected relationships between Arctic ecosystems and other marine environments. Discovering a previously unknown microorganism might introduce new biochemical pathways that help life survive extreme cold. Each discovery adds another piece to the puzzle of how life adapts to one of the harshest environments on Earth. Of course, not every future discovery will involve new species. Some will simply improve understanding of animals already known. For example, researchers still know relatively little about the life cycles of many deep Arctic fish. Certain species have been captured only rarely, leaving basic questions unanswered. Where do they reproduce? How long do they live? How do they survive during the long polar winter when food becomes scarce? Answering these questions requires patient observation and repeated exploration. The Arctic environment encourages this kind of slow scientific progress. Unlike regions where researchers can visit easily year-round, Arctic expeditions must work within narrow windows of opportunity. Each journey north becomes an important chance to gather new information, and every piece of information collected adds to a growing picture of the hidden ocean beneath the ice. Looking ahead, scientists believe the next several decades may bring more discoveries in the Arctic than all previous centuries combined. Advances in robotics, satellite observation, genetic analysis, and underwater mapping are expanding the reach of human exploration. Places that once seemed permanently inaccessible are gradually becoming easier to study. Yet even as technology improves, the Arctic will likely remain a place where nature retains some of its secrets. The ocean beneath the ice is vast, dark, and constantly shifting. Animals move through it quietly, following migration routes shaped by currents and seasons. Microorganisms drift through water layers carrying nutrients from one part of the ecosystem to another, and far below the frozen surface, across deep seafloor plains and hidden ridges, life continues evolving in ways that scientists are only beginning to understand. Some of the creatures waiting there may already exist in small populations that no camera has yet recorded. Others may appear unexpectedly when researchers explore a new valley or vent system. The Arctic Ocean has revealed many surprises so far, and beneath the drifting ice at the top of the world, there are still discoveries waiting that no human has seen yet. At first glance, the North Pole seems simple. A wide expanse of frozen ocean stretches across the top of the world, drifting slowly with currents and winds. Snow covers the ice in quiet layers. For much of the year, darkness settles over the region, broken only by faint starlight and the occasional glow of the aurora. From above, the landscape looks almost empty. Yet beneath that frozen surface lies an ocean that humans have only begun to understand. Every expedition into the Arctic reveals something new, not because the environment is constantly changing, but because so much of it remained hidden for so long. Even today, with satellites in orbit and advanced underwater vehicles capable of exploring the deep sea, the North Pole still keeps many of its secrets. Part of that mystery comes from the nature of the Arctic itself. Sea ice is never truly still. It drifts slowly across the ocean, pushed by wind and currents that move massive sheets of frozen water over great distances. A research station placed on one ice floe might travel hundreds of kilometers over the course of a year without anyone aboard noticing the movement. Beneath that drifting ice, the ocean is just as dynamic. Currents carry nutrients from distant seas. Tiny organisms bloom when sunlight returns after the long polar winter. Fish gather beneath ice ridges where food becomes concentrated. Whales pass through underwater corridors hidden from view. Much of this activity happens beyond the reach of direct observation. Scientists studying the Arctic often rely on brief glimpses rather than continuous monitoring. A remotely operated vehicle might descend into the water for a few hours. A hydrophone might record underwater sounds for several months before being retrieved. These fragments of information help build a larger picture, but the picture is still incomplete. There are entire regions of the Arctic Ocean where no research equipment has ever been deployed. Large sections of the seafloor remain mapped only in rough outlines. Underwater ridges, deep basins and hidden valleys stretch across the ocean floor, their ecosystems largely unknown. Even in areas that scientists have visited, discoveries continue. A camera lowered beneath the ice might capture an unfamiliar jelly drifting through the water column. A sediment sample might contain a tiny crustacean, unlike any previously described species. A genetic analysis of seawater might reveal microorganisms whose DNA does not match known organisms. Each discovery adds a small piece to the puzzle, but the puzzle itself remains far from complete. One reason the Arctic still holds secrets is the difficulty of working there. The environment challenges every piece of equipment brought into it. Temperatures drop far below freezing. Ice presses against ships and research stations. Storms sweep across the ocean with little warning. Even the simplest tasks can become complicated. Launching a submersible beneath sea ice requires careful planning to ensure that the vehicle can return safely through the same opening. Recovering instruments from drifting ice platforms may take days of searching. These challenges limit how often scientists can explore the region. Another factor involves time. Arctic ecosystems operate on rhythms that differ from those of more familiar environments. During winter darkness, biological activity slows. Animals conserve energy, and some descend into deeper water layers where conditions remain stable. When sunlight returns in spring, the ecosystem awakens quickly. Algae grow beneath the ice, plankton populations expand. Fish move toward feeding areas. Seals and whales follow the food. Many of these changes occur rapidly, sometimes within a few weeks. If researchers are not present during that window, important processes may pass unnoticed. There are also mysteries that scientists recognize but cannot yet fully explain. Strange acoustic signals recorded beneath the ice hint at animals or environmental processes that remain poorly understood. Occasional sightings of unfamiliar organisms suggest that some species have yet to be documented. Deep-sea ecosystems around hydrothermal vents and underwater ridges may host communities that no human has observed directly. Even the smallest organisms contribute to the unknown. Microbial life in the Arctic Ocean appears more diverse than previously believed. Each new genetic study reveals additional species of bacteria, algae, and microscopic protists drifting through the water. Many of these organisms perform chemical processes that scientists are still trying to understand. Because microbes form the base of marine food webs, their activity influences the entire ecosystem. Learning how they survive in freezing temperatures and low-light environments may reveal new aspects of biology. The Arctic also holds secrets related to its past. Layers of sediment on the ocean floor contain records of ancient climates. Tiny fossils preserved in those layers help scientists reconstruct how the region changed over millions of years. By studying these sediments, researchers learn about periods when the Arctic was warmer or colder than it is today. These discoveries help explain how life adapted to previous environmental changes. Yet even those records remain incomplete. Sediment cores collected from one location may represent only a small portion of the basin's history. Much of the Arctic seafloor still waits to be sampled. Another question scientists continue exploring involves the movement of animals beneath the ice. Whales travel through Arctic waters along routes that may span thousands of kilometers. Some species migrate between distant oceans, passing through narrow corridors where sea ice opens temporarily. Understanding these movements requires tracking animals over long periods. Satellite tags have provided valuable information, but many journeys remain only partially mapped. Fish movements beneath the ice are even harder to observe. Some species may travel along deep ocean currents or gather in specific regions during certain seasons. Without continuous monitoring, these patterns remain difficult to detect. The North Pole also keeps secrets simply because it is a place where human presence is rare. Unlike coastal seas where fishing vessels, research stations, and shipping routes create constant observation, the central Arctic remains largely untouched. Days may pass without any human activity in certain areas. In those quiet spaces, life continues following patterns shaped by evolution and environment rather than human attention. Animals hunt, migrate, reproduce, and disappear again into the darkness of deep water. Most of these events occur far from cameras or instruments. For scientists, this combination of vast space and limited observation creates both a challenge and an opportunity. Every expedition has the potential to uncover something unexpected. A new species might appear in a water sample. A deep-sea camera might record an animal rarely seen before. A hydrophone might capture sounds that lead researchers to study a previously unknown behaviour. The North Pole does not hide its secrets intentionally. They remain hidden simply because the region is enormous, complex, and difficult to reach. Exploration moves forward step by step. A few more kilometres of seafloor mapped, a few more species identified, a few more recordings analysed. Gradually, the hidden world beneath the ice becomes clearer. Yet even as knowledge grows, the Arctic retains something that has always defined it: distance from ordinary experience. Standing on the frozen surface of the North Pole, it is easy to imagine the ocean below as quiet and empty. But far beneath that ice, through thousands of meters of dark water, creatures move slowly across the seabed. Microorganisms drift through currents carrying energy through the ecosystem. Fish navigate along unseen ridges. Whales pass silently beneath drifting ice floes. Most of this activity remains unseen by human eyes, and for now, the Arctic Ocean continues to keep many of its secrets beneath the ice at the very top of the world.